Hello there, and welcome to Life Beyond Seen, where curiosity sinks slowly into the unknown and science drifts quietly like a tide meant to carry you toward rest. Tonight our journey takes us beneath the surface of the ocean into a world that has fascinated, frightened and baffled humans for as long as we have been gazing out at the waves. The deep sea, a place so immense and so alien that even now, after centuries of exploration, most of it remains a complete mystery. We've mapped the surfaces of Mars, we've tracked the movement of distant stars, we've pointed telescopes to galaxies millions of light years away, yet if you ask for a detailed map of the ocean floor beneath your feet right now, the truth is we couldn't give you one. The largest realm of our planet is still the least understood. But before we let ourselves descend, before we imagine what waits below those dark waters, I want to ask you something simple. Where are you listening from? Are you close to the sea? Maybe you can smell the salt air outside your window, or hear the crash of waves in the distance. Or perhaps you're far inland, surrounded by mountains or city streets where the ocean feels like another world entirely. No matter where you are, the deep sea is still part of your world. Its currents influence your climate. Its creatures balance ecosystems that ripple all the way to the surface. Its silence holds stories that affect each of us in ways we rarely think about. If you find this exploration soothing, or if it gives you that feeling of drifting while learning something new, I'd be so grateful if you tapped like or subscribed. It helps this quiet corner reach more people who might need a calm space to end their day. The ocean is vast, and sometimes the simple act of sharing curiosity can feel like tossing a light into the dark water, hoping it reaches someone else out there. So, let's settle in. Get comfortable. Let your thoughts slow down and drift with me. Because beneath the bright surface where the sunlight dances, beneath the waves that ships cut across, there stretches a hidden landscape bigger than all the continents combined. And somewhere down there in the quiet, in the crushing cold and the endless dark, lies the last true frontier of Earth. The first thing that strikes you when you think of the deep sea is its size. More than 70% of our planet is covered by ocean, and most of that ocean is deep. The abyssal zones, the trenches, the plains, they account for more than half the surface of Earth, yet we've seen only fragments. Scientists estimate that more than 80% of the ocean remains unexplored. To put that in perspective, imagine having a house where every room is locked except for one or two closets. That's about how much we've actually peeked at. For a species that prides itself on exploration, on climbing mountains and sending rovers to other planets, it's humbling to admit that our own world still hides so much right under our feet. Part of the reason the deep sea remains unknown is simple access. The ocean doesn't give up its secrets easily. The deeper you go, the harsher the conditions become. At the surface, waves and storms are challenge enough, but drop below a few hundred meters and sunlight begins to fade. By the time you reach 1 kilometer down, there is no natural light at all. Imagine standing in a cave where not a single ray of sun or moonlight has ever reached. That's the reality for most of the ocean. Then there's pressure. At just a few dozen meters below the surface, your ears start to feel the weight of the water. Keep going, and that pressure increases relentlessly. For every 10 meters you descend, it's like adding another full atmosphere of weight on your body. At 1,000 meters, the pressure is 100 times greater than at sea level. At the depths of the Mariana Trench, nearly 11 kilometers down, the pressure is more than 1,000 times what we feel at the surface. To put that into something more relatable, picture the weight of 50 jumbo jets pressing on your body. That's the kind of crushing force anything living or mechanical must endure to survive down there. Our technology has only recently begun to withstand those extremes. In 1960, Jacques Piccard and Don Walsh descended in the bathyscaphe Trieste into the Challenger Deep, the lowest known point of the Mariana Trench. Their vessel creaked and groaned the whole way down, and when they finally reached the bottom, the view was so clouded by disturbed sediment that they barely saw anything at all. Since then, a handful of other missions have returned, but each descent is a monumental effort requiring specialised engineering, extreme safety measures, and often millions of dollars. It's no wonder most of the seafloor remains untouched, and yet despite all these challenges, life thrives in the deep. That, perhaps, is the most astonishing fact. Where we might expect silence and emptiness, we find entire ecosystems, creatures that glow with their own light, fish with transparent bodies, giant squids that were once the stuff of sailors' nightmares but are now proven real. Down there, evolution has written its own strange rules. But I'm getting ahead of myself. Before we plunge into the lives of these strange residents, it's worth pausing to reflect on how strange it is that we know so little. Why is it that humanity, with all its satellites and sensors, hasn't devoted more energy to the deep sea? One answer lies in priorities. Space exploration captures imagination and funding in a way the ocean never quite has. There's something romantic about the idea of leaving Earth and looking outward, but inward, downward, beneath us, there's a world just as alien, just as filled with unknowns. Some argue it's even stranger, because it's right here and yet so inaccessible. When we think about the ocean from the shore, it's easy to picture it as a flat expanse. Blue water, maybe waves, maybe ships passing across it. But the reality beneath is closer to a mountain range turned upside down. The seafloor is covered in ridges, valleys, plains and trenches that rival anything on land. In fact, the tallest mountains and deepest canyons on Earth are underwater. The mid-ocean ridges, where tectonic plates pull apart, create mountain chains longer than any on land. The Mariana Trench drops deeper than Everest is tall. This hidden geography is so vast that even with modern sonar mapping, it will take decades before we can say we've charted it properly. And until we do, the deep sea will continue to feel like an undiscovered country. As you imagine this descent, picture the water around you shifting from blue to darker shades. Until the light is gone, imagine the silence, broken only by the creak of your vessel or the faint clicks of distant creatures using sound to navigate. It's not just dark, it's cold, near freezing in most places, the kind of cold that seeps into everything and slows it down. Down here, time itself feels different. Movements are slower, growth is slower, life takes on a rhythm that doesn't match the surface world. It's humbling to realise that this environment, which feels so hostile to us, is actually the largest habitat on Earth. More creatures live in the deep sea than in any other environment, though most of them have never been seen by human eyes. Every expedition brings back species that are new to science. Tiny shrimp with transparent bodies, fish with jaws that unhinge like something out of a nightmare, jellyfish that pulse with blue and green light. For them, this dark, pressurized, freezing world isn't strange at all. It's home. And maybe that's the heart of tonight's exploration. The deep sea remains unknown because it challenges us at every level, technologically, physically, emotionally. But it also remains unknown because it forces us to step outside our comfort zones. It asks us to imagine a world that doesn't operate by the rules we're used to. A world where light is rare, where sound carries farther than sight, where survival depends on adaptations so extreme they seem impossible. As we continue tonight, we'll travel deeper into this world. We'll look at why we know more about the surface of the moon than the seafloor beneath us. We'll meet the creatures that make their own light in the absence of the sun. We'll visit volcanic vents that host life forms capable of thriving without any sunlight at all. And we'll consider why, despite all our advances, we still hesitate to fully embrace the ocean as the frontier it is. So let's keep sinking. Not too fast, not with any rush, just slowly, carefully, letting the weight of water settle around us as the surface fades above. Somewhere below, in that quiet, is the mystery we came here for. When we think of Earth as a planet, most of us picture the land first. Continents, mountains, deserts, forests, cities. We imagine maps with familiar shapes, country borders traced neatly, roads and rivers drawn in lines we can follow, but those maps are illusions in a way. They show us only a fraction of what Earth truly is. Beneath all those coloured outlines lies a planet that is overwhelmingly ocean. More than 70% of its surface is covered by water, and most of that water is not the shallow coastal seas where people swim or fish or build harbours. It is deep, vast, and almost entirely hidden from our daily lives. When you take a globe in your hands and spin it, most of what you're seeing is ocean. Blue, unbroken, stretching in every direction. The deep sea isn't just a part of Earth. It is Earth's dominant feature, and yet we live as though it barely exists. Ask the average person to describe the Sahara Desert, and they can picture it. Endless dunes, scorching heat, camels crossing under a blazing sun. Ask them to describe Mount Everest, and they might mention snow-capped peaks, climbers with oxygen tanks, thin air at the summit. But ask the same person to describe the Abyssal Plain, or the Hadal Trench, or even what the ocean looks like 4 kilometres below the surface, and most will have no image at all. For most of human history, that absence of imagination has been understandable. We simply couldn't go there. But even today, with all the technology at our disposal, the deep sea remains more unknown than known. Scientists estimate that more than 80% of the ocean floor has never been mapped in detail. That means we don't just lack close-up images, we literally don't know the shape of most of it. Compare that to the Moon, which has been mapped almost completely by satellites. Compare it to Mars, whose valleys and mountains we know with high resolution. We know more about distant celestial bodies than about the bottom of our own seas. If you were to ask for a complete, accurate picture of the ocean floor, the truth is we don't have it. What we have are outlines, blurry scans, rough guesses filled in by computer models. The largest mountains, valleys and plains on our planet remain invisible to us, not because they're hidden by clouds or distance, but because they're drowned beneath kilometres of water. It's strange when you pause to think about it. We humans have always been explorers. We built ships to cross oceans long before we understood the size of those oceans. We trekked across deserts without knowing what lay beyond the horizon. We invented telescopes to see the stars, microscopes to see cells, cameras to preserve the fleeting present. Yet with all that curiosity, the deep sea has remained stubbornly out of reach. We've dipped into it, yes. We've sent submersibles down, dropped robotic vehicles, even sent divers with advanced suits. But compared to the scale of the deep, those are just pinpricks of light in a cavernous dark. Imagine walking through a vast forest and shining a flashlight at only a few trees. That's the equivalent of what we've done with the deep sea. Why does it matter though? If people live on the surface, if our farms and cities and daily lives are all above water, why should we care about what lies beneath? The answer is that the deep sea isn't just some alien place disconnected from us. It shapes our world in ways we often don't realise. The deep ocean is a regulator of climate. It stores immense amounts of carbon, absorbing heat and gases that would otherwise remain in the atmosphere. Its currents move like hidden rivers, transporting warmth and nutrients across the globe. Without those movements, the surface climate would shift dramatically, crops would fail, weather would grow extreme. In other words, the deep sea is part of the life support system of our planet. To ignore it is like ignoring your own lungs because you can't see them. There is also the matter of life. Scientists believe that as much as 2/3 of all species on Earth may live in the ocean, many of them in the deep. Every expedition into these depths seems to reveal new creatures. Jellyfish that glow with their own light, fish with bodies transparent as glass, worms that survive on chemical energy from the Earth's crust rather than sunlight. Some of these organisms could hold secrets to medicine, biology, or even technology. Bacteria that survive in high pressure might help us understand how to preserve materials. Enzymes from deep-sea creatures are already used in scientific research. But the truth is, we're only beginning to glimpse what's down there. It's as though someone opened a single drawer in a library of 1 million volumes and declared they had a sense of the whole collection. One reason the deep remains so mysterious is the sheer difficulty of getting there. Consider pressure again. At the bottom of the Mariana Trench, the pressure is about 8 tons per square inch. That's more than 1,000 times the pressure we experience at sea level. Any machine we send must be built like a fortress. A small crack, a flaw in the design, and the entire structure collapses instantly. Human divers cannot survive anywhere close to those depths without protection. The deepest dive by a human in a special submersible reached about 11 kilometers, but such missions are rare and costly. Sending unmanned vehicles is safer, but even those are limited by power, communication, and durability. The ocean does not welcome visitors easily. There is also darkness. Once you descend below about 200 meters, sunlight fades until it vanishes completely. No moonlight, no starlight, only blackness. To see anything, we rely on artificial lights, which can disturb or even frighten the creatures we hope to observe. Imagine aliens arriving on Earth shining searchlights brighter than the sun into our homes. It would not exactly encourage normal behaviour. Down there, most life has adapted to live without light altogether, or to create its own glow through bioluminescence. To us, the darkness is an obstacle. To them, it is simply the environment. Temperature adds another challenge. Deep sea water is near freezing in most places, hovering around 2 to 4 degrees Celsius. At hydrothermal vents, it can surge to hundreds of degrees, but only in pockets. Most of the abyss is cold enough to slow metabolism, slow growth, slow everything. A fish may take decades to reach maturity. A coral reef in the deep sea may grow only a centimetre a year. Entire ecosystems operate on timescales unfamiliar to us, as though the deep sea keeps its own clock, one that runs much slower than the one we use at the surface. And then there is scale. The deep ocean is not just deep. It is vast in every horizontal direction. The abyssal plains stretch for thousands of kilometres, as flat and featureless as deserts. Trenches cut into the seafloor like scars. Ridges rise like mountain chains. The sheer size means that even if we had perfect machines to explore, it would take centuries to survey it all. We're dealing with an environment so large that it humbles our attempts to measure it. Yet despite all of this, our ignorance is not complete. We know enough to sense that what lies beneath is extraordinary. We know enough to be tantalized. Sonar scans reveal hints of massive structures. Volcanoes taller than Everest, canyons deeper than the Grand Canyon, seamounts scattered like uncharted islands. We have filmed creatures that look like science fiction brought to life. We have discovered hydrothermal vents that host entire ecosystems independent of the sun. Every fragment of knowledge suggests there is much more waiting, and that is why the deep sea is called Earth's last frontier. It is the one place left where the unknown is not only possible but guaranteed. It's easy to forget how little we know because the ocean feels familiar on the surface. We swim in it, we fish from it, we sail across it. But familiarity is deceptive. Beneath those waves lies something closer to an unexplored planet. To call it the vast unknown beneath our feet is not exaggeration. It is literal. Right now, under your feet, under my feet, under every coastline and every horizon, there are worlds we have never seen. And it makes you wonder, how much of our history, our myths, our fears have been shaped by that ignorance? For centuries, sailors told stories of monsters from the deep, krakens that could swallow ships whole, serpents that stretched across the horizon. At the time, people may have dismissed those tales as superstition, but now we know there are creatures down there that stretch longer than buses, squids with eyes the size of dinner plates, sharks older than human civilizations. Perhaps the gap between myth and reality is not so wide after all. The deep sea reminds us that mystery still exists. In a world where satellites give us street views from anywhere on land, where we can zoom into almost any place on Earth with a swipe of our fingers, the ocean still says no. It refuses to be mapped easily. It refuses to be reduced to convenience. It holds back its secrets, offering them only to those willing to struggle for them. and maybe that's why it still captures imagination. In a way, it protects us from the illusion that we already know everything. As we continue, keep in mind this simple truth. The deep sea is not some separate alien realm. It is Earth itself. Most of our planet is hidden from us, and the vast unknown beneath our feet is not a poetic phrase. It's reality. If we want to understand this planet, our home, we cannot stop at the shore. We have to look down into the darkness and accept that the journey will take patience, ingenuity, and maybe even a little humility. And so, our descent continues, deeper into this enormous unknown, where each meter down brings us closer to environments we barely understand. It often surprises people when they first hear it, but it's true. We know more about the Moon, a barren rock orbiting nearly 400,000 kilometers away, than we do about the oceans that cover most of our own planet. At first, that sounds almost ridiculous. How could something so distant be more familiar to us than the water that laps at our shores every day? The answer is a mix of technology, priorities, and the peculiar way humans choose where to focus their curiosity. The Moon, for all its distance, is easy to look at. We can stand on Earth and see it with the naked eye. It doesn't hide behind anything, and light reflects off its surface clearly enough for telescopes to capture details from afar. Long before rockets and satellites, astronomers could map its craters with remarkable precision. By the time the 20th century arrived, the Moon had been charted in detail, even though no one had set foot on it. With the space race, billions of dollars and the full weight of national pride went into studying it. We launched probes, orbiters, and eventually people, all with the goal of claiming that barren surface as a milestone in human achievement. The ocean, on the other hand, resists easy observation. You can stare at it from the shore, but the surface reveals nothing of what lies beneath. Light doesn't pass through it beyond a few hundred meters. Radio waves, the same signals we use to talk to spacecraft, fade away in seawater. Telescopes cannot pierce it. From above, the ocean is a mirror, and beneath that mirror lies a world that hides itself by nature. To map it requires different tools, and those tools are far harder to use than rockets pointed at the sky. Satellites can and do help us study the ocean, but mostly they measure its surface, its colour, its waves, its temperature, its height. They cannot see the seafloor directly. What we know of the deep ocean floor largely comes from sonar mapping, bouncing sound waves off the bottom and measuring how long they take to return. Ships towing sonar can build detailed maps, but here's the catch. A single ship can only map a narrow strip at a time. To cover the entire ocean floor with high-resolution sonar would take hundreds of years of continuous effort and staggering amounts of funding. And unlike the moon landing, there has never been a global competition or geopolitical drive to make it happen. It's not that we couldn't. The technology exists. The difficulty is in scale. The ocean is vast, and mapping it with the resolution we take for granted on land is a monumental task. When satellites mapped the moon, they did it in broad sweeps, covering the whole surface quickly because there was no atmosphere or water to interfere. With the ocean, every kilometre requires careful passes, every depth a new challenge. We have detailed maps of less than 20% of the seafloor, and even those are incomplete. The rest is filled in with models, guesses based on gravity measurements, and interpolations. In short, we're looking at blurry outlines where sharp detail should be. Another factor is danger. Sending a probe to the moon is costly, yes, but once it's there, it doesn't have to deal with crushing pressure or corrosive salt water. Machines in space can fail and drift quietly forever, but machines in the ocean are destroyed instantly if anything goes wrong. Every expedition into the deep is a risk. Engineers must design submersibles with walls thick enough to withstand tons of pressure, seals that won't leak, systems that can operate in near freezing darkness. And if something does fail, the machine cannot be retrieved easily. It's swallowed by the sea. That risk adds cost, and cost narrows ambition. Then there's human psychology. The moon is visible. It inspires poetry, songs, stories. Looking at it stirs imagination. The ocean does as well, but in a different way. Its surface is familiar, even comforting, yet what lies below feels alien in a way that doesn't always attract the same drive. Politicians were willing to spend billions to put flags on the moon because everyone could see the goal. Convincing those same people to spend billions on mapping a dark seafloor no one will ever look at directly is a harder sell. Even today, space exploration often wins funding and attention over ocean science. The unknown above feels more glamorous than the unknown below, but if you compare them objectively, the deep sea is stranger, and in many ways more alien than the moon. The moon is a dead world. Its surface is rock, dust, craters, nothing more. The ocean, by contrast, is teeming with life in forms we still don't fully understand. It has landscapes shaped by tectonics, volcanoes, trenches and ridges. It has rivers and lakes made of brine sitting within the water, waterfalls that tumble from one density of liquid to another, currents that circle the globe like invisible conveyor belts. It has creatures that light themselves like lanterns, others that drift like ghosts, others that withstand pressures that would crush steel. By any measure, the ocean is the more remarkable frontier, and yet the moon holds more detailed maps. Think of it this way. If you wanted to walk across the moon, you could plan your route with precision. You'd know where the craters are, the mountains, the plains. If you wanted to walk across the seafloor, even in shallow seas, you'd be navigating blind most of the way. Fishermen sometimes pull up nets snagged on undersea cliffs no one knew were there. Submarine cables have to be laid carefully because the terrain is unpredictable. Planes that crash into the ocean can take years to locate because the seafloor in those regions is unknown. This isn't an exaggeration. When Malaysia Airlines Flight 370 disappeared in 2014, the search highlighted just how poorly mapped the southern Indian Ocean was. Entire regions had to be charted for the first time, and even then the wreck was not found. That kind of event would never happen on the moon. If something crashed there, we could locate it within hours using existing maps. So why hasn't this imbalance been corrected? Part of the reason is that mapping the ocean doesn't seem urgent until it is. A missing plane, a submarine accident, an undersea earthquake. These remind us how little we know, but once the crisis passes, the urgency fades. Space exploration, on the other hand, is framed as progress, the next step for humanity. The ocean feels like something we already conquered, even though we barely touched it. Culturally, we see it as background, as scenery, not as frontier. That perception has slowed the momentum of discovery, and yet, things are changing slowly. Projects like Seabed 2030 aim to map the entire ocean floor in detail by the end of this decade. Advances in autonomous underwater vehicles, drones and improved sonar are making it more feasible. Still, even if those efforts succeed, the gap between how we see the moon and how we see the ocean remains. One is a place we dream of colonizing, of mining, of living on. The other is a place where we hesitate to venture, as though its very vastness intimidates us. Perhaps there is also something subconscious at play. The ocean touches primal fears in ways the moon does not. Falling into the sea means drowning, vanishing beneath the waves. It means entering an environment where we cannot breathe, where predators might wait unseen. The moon may be lifeless, but it does not trigger those instincts. We can picture walking on its surface. We can't as easily picture walking calmly on the abyssal plain with kilometers of water pressing down above us. The mystery of the ocean is both alluring and unsettling, which may explain why humanity has often chosen to look upward rather than downward. Yet ignoring it doesn't change reality. The ocean is here. It shapes the climate, feeds billions of people, regulates the cycles of Earth itself. It hides resources, mysteries, and perhaps entire categories of life we have yet to imagine. To know less about it than about the moon is more than ironic. It's a reminder of how incomplete our understanding of our own planet really is. Every time we launch a mission to space, we should remember there is an equally vast mission waiting right here, beneath our feet, hidden by water and darkness. It is worth asking what might change if we devoted even half the energy we spend on space to the ocean. What discoveries would we make? How many new medicines, technologies, or insights into climate would emerge? How many mysteries would dissolve under the light of knowledge, and how many new ones would appear in their place? Exploration doesn't diminish wonder, it deepens it. When we mapped the moon, we didn't lose its beauty, we gained a deeper respect for its place in the cosmos. The same could be true for the ocean. Knowing its contours, its ridges, its trenches would not make it less mysterious. It would make it more real, more present, more connected to our lives. For now, though, we live with the paradox. A lifeless rock in space is familiar, while the living heart of our own planet remains unknown. The moon has been walked on, photographed from every angle, studied endlessly. The ocean, larger and more complex, remains hidden in shadow. And until we change our priorities, that imbalance will continue. But even without complete maps, even with blurred outlines and unanswered questions, we can still imagine. We can still peer into the darkness with cautious curiosity. We can still lower machines into the deep and be astonished by what they reveal. Each fragment of knowledge, each expedition, is like a candle lit in a cavern, revealing just enough to remind us how much more lies beyond. The comparison to the moon isn't meant to diminish our achievements in space. It's meant to remind us that the greatest unknown might still be right here, not above our heads, but beneath the waves. And so we keep drifting downward, past the surface where sunlight glitters, into the darkness where mystery thickens. The deeper we go, the more the ocean demands of us, and the more it offers in return. When you think about why the deep sea is so hard to reach, the word that comes to mind almost immediately is pressure. It's invisible, silent, and constant, yet it is the greatest guardian of the abyss. Unlike darkness, which we can solve with lights, or distance, which we can solve with travel, pressure is an obstacle that pushes back with unimaginable force. It doesn't just resist, it crushes. It reshapes matter. It decides who or what can exist in the deep, and who cannot. At sea level, the pressure around us is something we barely notice. The weight of the atmosphere presses on every square inch of our skin with about 14 pounds of force. We live in it comfortably, our bodies balanced with it. We breathe, we move, we never give it much thought. But descend into water and things change quickly. Water is heavy, far heavier than air, and it stacks upon itself relentlessly. For every 10 meters you dive, another full atmosphere of pressure is added. At 100 meters down, the pressure is already 10 times what you feel on land. That's enough to begin affecting even trained divers, who must carry specialized equipment to survive. But 100 meters is nothing compared to the real depths. Drop to 1,000 meters, and the pressure is about 100 times greater than at the surface. At the bottom of the Mariana Trench, nearly 11,000 meters down, the pressure is over 1,000 times stronger. Imagine the weight of 50 jumbo jets pressing down on your body at once. Imagine a steel container collapsing like a soda can under a boot. That is what pressure does in the abyss. It is not a slow squeeze, it is instant destruction for anything unprepared. Machines designed to explore these depths must be built like fortresses. Submersibles are engineered with spherical chambers, because spheres distribute pressure evenly. Walls are made thicker than you might expect, using materials designed to resist cracking. Even then, every descent is nerve-wracking. A single weakness, an unnoticed flaw, can spell disaster. When Jacques Piccard and Don Walsh descended in the bathyscaphe Trieste in 1960, they heard the hull creak and pop under the strain. A window cracked during the descent, though it held long enough to bring them back alive. Every mission since then has carried that same reminder. Pressure is not forgiving. For living creatures, pressure is not just a barrier. It is the environment itself. Life in the deep sea has had millions of years to adapt, and those adaptations are astonishing. Many deep-sea organisms have no air pockets in their bodies. Fish at the surface rely on swim bladders filled with gas to control buoyancy. But gas is easily compressed. At depth, a gas-filled organ would collapse, so deep-sea fish use fat, oils, or other mechanisms to maintain buoyancy instead. Their bodies are soft, flexible, and often gelatinous, designed to bend with the pressure rather than resist it. To us they look strange, sometimes ghostly, sometimes fragile, but those features are what let them survive. It's easy to assume that such creatures must be delicate, that they could not survive near the surface. And often that's true. Many deep-sea animals brought up to the surface die not from lack of oxygen or food, but from the sudden release of pressure. Their bodies rupture, their organs expand uncontrollably. It's a reminder that pressure shapes life in profound ways, not just physically, but at the cellular level. Proteins, enzymes, and membranes in deep-sea organisms are built to function under conditions that would render ours useless. Studying them reveals not just curiosity, but potential insights into biochemistry. Some researchers hope these adaptations might one day inspire medical or industrial advances. Pressure also changes the way sound travels. In the deep, sound waves move faster and farther than at the surface. Whales, for instance, take advantage of this by communicating across vast distances. Scientists believe some whale songs can travel thousands of kilometers, echoing through channels shaped by temperature, salinity, and pressure. For humans, this means sonar signals can bounce in unexpected ways, creating illusions, false echoes, or mysterious noises. Some of the strangest unexplained sounds recorded in the ocean may owe their character to how pressure bends and distorts vibrations in the water. For human exploration, pressure is perhaps the most limiting factor of all. Divers can only descend so far before their bodies begin to suffer. Beyond a few hundred meters, human physiology simply cannot cope, even with special breathing gases. Submarines and remotely operated vehicles can go deeper, but each must be designed to withstand forces that increase relentlessly the farther down they go. There is no plateau where the pressure stops building. It is always more, always heavier, until the seafloor itself provides a bottom. Consider what this means practically. Sending a spacecraft to the moon requires breaking free of gravity and travelling through the vacuum of space. It is difficult, but the environment once reached is empty. In contrast, sending a submersible to the bottom of the ocean means descending into an environment that grows increasingly hostile every step of the way. The deeper you go, the harder it gets, until finally you are in a place where pressure is so great that even steel struggles. That is why, more than 60 years after the first descent to the Challenger Deep, fewer than a handful of missions have returned. Far more people have been into space than have visited the deepest parts of the ocean. Pressure is the reason. It also affects how we imagine the deep. Stories of monsters, of crushing darkness, of ships swallowed whole, all of them carry an undercurrent of this invisible force. Sailors may not have understood the numbers, but they sense the truth. The ocean holds weight beyond comprehension. To descend into it without respect is to invite disaster. Even modern submariners carry that knowledge. Every time they dive, they are acutely aware of the tons of water pressing against the hull. They trust engineering, but they also know the ocean has no tolerance for mistakes. And yet, pressure is not always the enemy. In its way, it is also a sculptor. It shapes the seafloor, it governs the currents, it even influences the chemistry of the water. At great depths, pressure affects how gases dissolve, how minerals form, how vents release their energy. It creates environments where life must invent new strategies, leading to some of the most remarkable adaptations known on Earth. The very strangeness of deep-sea creatures is a testament to pressure's role. Transparent skin, glowing organs, oversized jaws, all of it is shaped by the relentless squeeze of the abyss. For us, though, pressure remains the Great Wall. It explains why we cannot simply dive freely to the bottom, why our machines must be overbuilt, why our maps are incomplete. It is the reason the deep sea remains so mysterious even in the 21st century. Until we master it, or rather, until we learn to work with it, much of the ocean will remain hidden. And so, as we sink deeper in thought, it becomes clear that every metre of water is not just distance. It is weight. It is resistance. It is the ocean itself reminding us that its secrets will not be given lightly. Pressure guards the deep, and in doing so, it keeps the mystery alive. If pressure is the invisible hand that squeezes everything in the deep, then darkness is the silence that cloaks it. It begins sooner than most people realise. Slip beneath the surface on a sunny day, and for a few metres the water glows with scattered light, ripples shimmering like glass. By 20 or 30 metres down, the glow begins to fade. By 200 metres, sunlight can no longer penetrate, and past that, the ocean is black. Not dim, not shadowed, completely, utterly black. For most of the ocean, nearly 90%, this is the reality. A world where no ray of the sun reaches, where night is not a passing phase but a permanent condition. If you were placed there without lights, your eyes would see nothing, not even your own hands. The concept of day and night disappears. The only cycles are those of currents, of drifting particles, of faint chemical changes. For creatures adapted to this environment, darkness is not unusual. It is normal. For us who live our lives guided by light, it is profoundly alien. Darkness changes everything. On land, vision dominates. We see the world in colour, in shape, in detail. We rely on sight more than any other sense. But in the deep sea, vision is useless without light to reflect. So life has followed other paths. Some creatures develop enormous eyes, attempting to catch whatever rare photons might drift down. Others abandon vision altogether, evolving blind or nearly blind, relying on touch, vibration, or chemical signals instead. And many turn to an astonishing adaptation: bioluminescence. Before we imagine those glowing beings, it's worth pausing on what it means for light to vanish so completely. Sunlight doesn't just let us see, it powers life. Photosynthesis, the process by which plants and algae turn light into energy, underpins nearly every ecosystem we know. Remove sunlight, and that entire chain collapses. That's why for so long scientists believed the deep sea would be barren. They assumed no sunlight meant no energy, no plants, no animals, nothing but empty water. What they found instead was life. But life running on different rules. The creatures that live in this endless night feed in unusual ways. Some drift upward at dusk to graze on the microscopic algae that bloom near the surface, then return to the depths by dawn. This daily migration, called the Deal vertical migration, is the largest animal movement on Earth, happening every single day as billions of fish, shrimp, and other creatures rise and fall with the sun's faint glow. Others feed on the slow rain of organic material that drifts down from above. Tiny particles, bits of dead plankton, scales, feces. It is called marine snow, and though it sounds delicate, it is the foundation of deep sea food webs. Piece by piece, flake by flake, it delivers sustenance into the dark. But darkness doesn't just shape food chains, it shapes form. Look at photos of deep-sea fish and you'll notice they often look bizarre compared to surface species. Some are almost transparent, their bodies reduced to the bare essentials since camouflage in pitch blackness is irrelevant. Others are jet black or red, colours that render them invisible, because red light is the first wavelength lost as you descend. What appears bright red near the surface is simply black in the abyss. Some creatures grow enormous mouths relative to their size, able to gulp down prey whenever chance allows, since meals are rare and unpredictable. Others grow long, delicate feelers or sensitive lateral lines to detect the faintest movement in the water. All of it is shaped by the same reality. In the absence of light, Every survival strategy must adapt to darkness. It also affects behaviour. On the surface, predators rely on vision to chase, capture and ambush. In the deep, predators stalk in silence. They lure with glows, they feel with currents, they wait with patience. Prey species too adjust. Some dart at the slightest vibration, others drift slowly, conserving energy until food is available. Even communication changes. While surface creatures often display colours or patterns, deep-sea creatures may signal with flashes of bioluminescence instead. Entire conversations happen in pulses of blue-green light invisible to us without special equipment. Humans exploring these depths are reminded instantly of the power of darkness. Submersibles turn on their lights, and the beams reveal a narrow cone, nothing beyond. It is like driving a car at night through an endless desert with no landmarks, no horizon, only what the headlights catch. Switch the lights off, and you're left in pure blackness, where up and down blur into irrelevance. It's easy to lose sense of direction, of scale, of distance. The ocean doesn't just hide what is far away. It hides what is close, until it is right upon you. This darkness explains too why the deep sea remained unknown for so long. Our ancestors could map stars, mountains and deserts because they could see them. They could not see beneath the waves. When they imagined monsters lurking there, it was not just fear, it was a logical conclusion. Darkness conceals, and the mind fills that void with shapes and stories. Even now, with cameras and lights, we struggle. Cameras can only capture what we point them at. Lights reveal only a fraction of what surrounds them. Vast regions remain unseen, not because we aren't looking, but because there is nothing for our eyes to catch. Yet despite the absence of sunlight, the deep is not empty of light altogether. Bioluminescence fills the void with a strange, beautiful substitute. Tiny plankton spark when disturbed, leaving trails like stars in the water. Fish dangle glowing lures from their heads. Jellyfish pulse with waves of light across their bodies. Shrimp eject glowing clouds to distract predators. The darkness is their canvas, and light is their tool. In some regions, it's estimated that more than 90% of animals produce light of some kind. Imagine walking through a forest at night, where nearly every plant and animal glowed faintly. That is closer to the reality of the deep ocean than endless black. For humans, though, the absence of sunlight changes more than vision. It changes psychology. We are creatures of light cycles. Our circadian rhythms depend on the rising and setting of the sun. In darkness, those rhythms falter. Submariners, cave dwellers, and astronauts all know the disorienting effects of losing track of day and night. In the deep, there is no dawn to reset the clock. Machines and explorers must carry their own rhythms artificially, or risk losing themselves to timelessness. Even descriptions of dives into the abyss often mention how time feels distorted. Without visual cues, minutes stretch or collapse. The brain cannot anchor itself, and darkness becomes not just an absence, but an environment of its own. Darkness also plays a role in preserving history. Sunlight breaks down objects, bleaching bones, degrading wrecks. In the deep, absence of light slows that process. Shipwrecks can remain for centuries almost untouched, preserved in cold darkness. Creatures colonize them slowly, but without sun, without rapid decay, they endure as silent museums. Submarines lost in war, ancient vessels from trade routes, even airplanes, all rest in darkness, shielded from time by absence of light. To find them requires technology, but when found, they tell stories preserved better than many things on land, and perhaps this is the paradox of deep-sea darkness. On one hand, it makes exploration difficult, even impossible without artificial aid. On the other, it creates conditions where life invents extraordinary solutions and where history lingers quietly. What we fear as emptiness is, in reality, a different kind of fullness. The absence of sunlight does not mean the absence of life or wonder. It means a different order, one that is harder for us to grasp because we are creatures of the surface. As we continue deeper, it is worth holding on to that thought. Darkness in the ocean is not emptiness. It is not silence. It is an environment rich with adaptations, with signals, with mysteries we are only beginning to decode. Pressure may crush, but darkness conceals and reveals in equal measure. The deep ocean is a world built not around what the sun gives, but around what life invents when the sun disappears. And so the descent continues, from pressure to darkness, from absence of light to the strange ecosystems that thrive without it, guiding us further into the unknown where life glows, flickers, and survives against all odds. When we talk about the ocean, it is tempting to imagine it as one continuous body of water, the same from top to bottom. But just like the atmosphere has layers, with clouds forming at one height and jet streams racing at another, the ocean is divided into distinct zones. Each one has its own character, its own conditions, its own kind of life. These layers are not arbitrary. They are dictated by sunlight, temperature, pressure, and depth, shaping the sea into a vertical world stacked upon itself. To understand the deep sea, we first need to understand this staircase of water, from the surface where the sun touches down to the abyssal plains far below. At the very top is the epipelagic zone, often simply called the sunlight zone. This extends down to about 200 meters, and it is the ocean most people know. Sunlight penetrates here strongly enough to support photosynthesis, so algae bloom in abundance. Fish dart in schools, seabirds dive, corals grow in warm shallows, and humans swim, fish, and sail across it. Nearly all of human activity with the ocean takes place in this layer. Bright, colourful reefs, coastal fisheries, and surface-dwelling creatures like dolphins and turtles belong here. The abundance of light makes it the most familiar and most productive zone. But sunlight is not endless. Below 200 meters, brightness fades into twilight. This region, the mesopelagic zone, stretches down to about 1,000 meters. Sometimes called the twilight zone, it is a place of dim blue light, faint and eerie. Sunlight is too weak here for photosynthesis, so no plants grow, but enough light filters down to create a strange half-world. Many creatures of this zone migrate upward at night to feed in the richer surface waters, then retreat by day to avoid predators. Lanternfish, squid, and countless others follow this daily cycle. Bioluminescence becomes more common here, filling the dimness with sudden sparks and flashes. It is also the depth where predators with oversized eyes and sensitive organs hunt for any trace of movement. Humans rarely visit this zone directly, but it may be one of the most important layers on Earth because it acts as a conveyor, moving carbon and nutrients from the surface downward in massive daily migrations. Beneath the twilight lies the midnight zone, the bathypelagic. From 1,000 meters down to around 4,000, sunlight is completely absent. This is true darkness. Pressure here is immense, and temperatures hover near freezing. The creatures that live here have long since given up on vision as we know it. They rely on touch, vibration, or their own bioluminescent signals. This is the realm of anglerfish, with their eerie glowing lures, and of giant squid drifting silently in the dark. Food is scarce, so most organisms here conserve energy, moving slowly, eating opportunistically. The silence is broken only by faint vibrations or the occasional glow of a passing animal. Farther still, from 4,000 meters down to 6,000, is the abyssopelagic zone. Its name comes from the Greek word meaning bottomless, and the word fits. It covers vast abyssal plains, flat stretches of seafloor that seem endless. The water here is almost uniformly near freezing, the pressure hundreds of times greater than at the surface. Few creatures are found, but those that do live here are adapted to the extreme. Sea cucumbers crawl across the mud, brittle stars wave delicate arms, and strange fish lurk, their lives slow and steady. The abyss is the single largest environment on Earth, covering more area than all the continents combined, and yet it is also the least explored. To picture it, imagine deserts so vast they span the planet, but in place of sand there is mud and silt, and above them eternal blackness. That is the abyss. And deeper still lies the Hadal Zone, beginning at 6,000 meters and descending into the trenches, the deepest parts of the ocean. Named after Hades, the underworld of Greek mythology, this zone is found only in narrow places where tectonic plates collide and one slides beneath another, carving trenches that plunge into the crust. The Mariana Trench is the most famous, but there are many others scattered around the globe. Life here is sparse, but not absent. Amphipods, snailfish and microbes thrive where nothing should. Hydrothermal vents sometimes punctuate the darkness with bursts of mineral-rich water, creating pockets of thriving ecosystems in the unlikeliest of places. Few humans have ever visited these depths, and each descent has revealed surprises. The Hadal Zone remains perhaps the most mysterious of all, a realm where even our machines struggle to endure. These layers may sound like boundaries on a map, neat and fixed, but the reality is more fluid. Temperature, salinity, and currents all shift the exact limits, blending one zone into the next. Still, the general structure holds, and life is organized accordingly. Each layer has its own inhabitants, its own survival strategies, its own strange beauty. Together they form a vertical ecosystem unlike anything on land. For humans trying to study the ocean, these layers act like levels of challenge. The surface is easy. We can swim, sail, and dive there with minimal equipment. The Twilight Zone requires advanced technology, robotic vehicles, or specialized submersibles. The Midnight and Abyssal Zones demand machines built to endure crushing pressure and complete darkness. The Hadal Trenches require the very best engineering we can produce, and even then descents are rare. It is as though Earth itself has created a gauntlet, testing how far we are willing to go. Each layer is a new threshold, each threshold more difficult than the last. But the layers are not just barriers, they are ecosystems of staggering scale. The Twilight Zone, for example, may hold more fish biomass than all the rest of the ocean combined, yet we know little about it. Fishing there is difficult, and so most of it remains untouched. Some scientists warn that commercial exploitation could collapse it before we even understand it, much as has happened with surface fisheries. The Abyss too is home to strange mineral deposits, including manganese nodules and hydrothermal vent fields, which corporations now eye for deep-sea mining. Yet disturbing these fragile environments without fully understanding them risks consequences we cannot predict. The layers of the ocean are not just abstract categories. They are real, functioning systems that shape climate, biodiversity, and the future of our planet. For those who explore, moving between layers is like passing through worlds. Divers who go beyond recreational depths describe the Twilight Zone as eerie, a place where the light fades and colours vanish. Submersible pilots descending into the Midnight Zone describe a sudden shift. The moment the last trace of sunlight disappears and the outside world becomes absolute black. Scientists who visit the Abyss often compare it to standing on an alien planet, so empty and vast that it feels endless. And those few who have reached the trenches often return with a sense of awe, humbled by the scale and silence. Each layer strips away something familiar. First colour, then light, then even the concept of day and night, until what remains is pure otherness. And yet, in all of them, life persists. From the bustling reefs of the Sunlight Zone to the ghostly fish of the trenches, evolution has found ways to fill every space. Some adaptations are ingenious, some bizarre, some unsettling, but all testify to the resilience of life. To map the ocean's layers is not just to draw lines of depth. It is to acknowledge that Earth is a stacked world, a planet where ecosystems exist not only across space but across depth, layered like pages in a book that most of us have never read. The more we descend, the more those layers feel like thresholds of mystery, each one holding back more secrets than the last. And so, From the glowing surface where waves glitter in sunlight, we travel down through twilight, into midnight, across the abyss, and finally into the trenches, where the weight of the world presses hardest and the mysteries are deepest. Somewhere between the brightness of the surface and the black silence of the deep lies a band of ocean that feels like its own hidden universe. Scientists call it the Mesopelagic Zone, but it's more often known by a name that feels closer to its truth, the Twilight Zone. It stretches from about 200 meters below the surface to around 1,000 meters down. Too deep for sunlight to support photosynthesis, but not so deep that all light disappears. It is a place of half shadows, of dim blue that fades with each meter, of strange silhouettes that drift like ghosts. If the surface ocean is familiar and the abyss is alien, then the Twilight Zone is the bridge, where life reveals forms that seem to belong to both worlds and yet to neither. What makes the Twilight Zone so strange is not just the way it looks, but the way it functions. In a sense, it is the great middle child of the ocean, not as accessible as the surface, not as extreme as the abyss, often overlooked, yet quietly one of the most important habitats on Earth. In fact, it might be the single largest living space for fish and other organisms. Billions upon billions of animals inhabit it, forming the backbone of one of the greatest migrations on the planet, a migration that happens not once a year, not once a season, but every single night. As the sun sets and darkness spreads over the surface, creatures of the Twilight Zone begin to rise. Tiny plankton, small fish, shrimp, squid, and countless others ascend toward shallower waters to feed on the rich layer of microscopic algae that bloom where the light still reaches. As dawn approaches, they descend again, retreating into the safety of dimness. This daily cycle, called diel vertical migration, involves more movement of biomass than any other migration on Earth, far surpassing wildebeests crossing Africa or birds flying across continents. And yet, few people have ever heard of it. While we marvel at flocks in the sky, the largest animal movement on the planet happens silently, invisibly beneath the waves. The creatures that participate in this cycle are bizarre in appearance and ingenious in adaptation. One of the most common is the lanternfish, a small, unassuming species covered with tiny organs that emit light. They use these lights for camouflage, counter-illumination, masking their silhouettes against the faint glow above. To a predator below, looking up, a lanternfish lit from beneath blends into the dim light filtering down. It is a remarkable trick, and one that shows how even a small amount of sunlight still shapes life. Lanternfish are also astonishingly abundant. Some estimates suggest they may be the most numerous vertebrate on Earth, with trillions of individuals in the oceans. Despite their importance, they remain little known, their lives hidden by the depth at which they dwell. Other Twilight Zone creatures embrace the darkness fully. The hatchetfish, with its thin, reflective body, looks like a sliver of metal. Its eyes bulge upward, scanning for the faint silhouettes of prey above. Its body glimmers faintly, reflecting what little light penetrates, making it nearly invisible. Then there are bristlemouths, small fish with mouths disproportionately large for their size, lined with needle-like teeth. They wait with patience, snatching whatever prey drifts by. Bristlemouths may rival lanternfish in abundance, forming a biomass so immense that if gathered together, it would outweigh all the cattle on land. The Twilight Zone is also home to creatures that feel almost mythological. Take the dragonfish, with its elongated body, enormous fangs and glowing barbel that dangles from its chin like a fishing rod. It uses its light to lure prey closer, then snaps its jaws shut with terrifying speed. Some dragonfish can even produce red bioluminescence, a rarity in the ocean. Because red light disappears first with depth, most deep-sea animals cannot see it. Dragonfish use this invisible flashlight to hunt stealthily, illuminating prey without being noticed. It is one of nature's cleverest tricks, hidden in the twilight. Squid too are common in this zone, from tiny species no larger than your finger to giants that grow longer than buses. Many use jet propulsion to dart away from predators, leaving trails of light instead of ink confusing their pursuers. Some squids' bodies shimmer like mirrors, reflecting the faint blue around them so perfectly that they seem to vanish. Others pulse with light in dazzling displays, communication or camouflage or simply survival. The twilight zone is not only about predators and prey, it is also about balance. This zone plays a critical role in the Earth's carbon cycle. When organisms feed near the surface at night and return to depth by day, they transport carbon downward, locking it away in deeper waters. The fecal pellets they produce, the bodies that sink when they die, all contribute to what scientists call the biological pump. This process helps regulate climate by moving carbon out of the atmosphere and into long-term storage. Without it, our world would likely be far warmer, our atmosphere far more unstable. The twilight zone, in other words, is not just strange, it is vital. Yet despite its importance, it remains poorly understood. Sampling it is difficult. Nets can capture some creatures, but many are delicate, collapsing into mush when brought to the surface. Lights from submersibles often startle or scatter animals, altering their natural behaviour. Cameras capture glimpses, but never the whole. Most of what we know comes from fragments, from the occasional dive, from instruments lowered in darkness. Whole categories of life may still be hidden there, undiscovered, unclassified, waiting. The twilight zone is one of the ocean's greatest reservoirs of mystery precisely because it lies just beyond easy reach, close enough to sense, too far to grasp completely. And then there are the giants. Sailors once spoke of colossal squids dragging ships beneath the waves. For centuries those were only myths, but in recent decades, evidence has confirmed their existence. Colossal squid, with eyes the size of dinner plates and tentacles lined with hooks, inhabit the twilight and deeper zones. Rarely seen alive, they hint at battles with sperm whales, whose scars often bear the marks of tentacle suckers. To glimpse one of these creatures in the wild is to realise how much of legend is rooted in truth. The twilight zone hides giants we barely comprehend. Life here is shaped by scarcity as much as by abundance. Food is plentiful only at certain times. So many creatures have developed oversized jaws, expandable stomachs, or the ability to eat prey nearly as large as themselves. Energy conservation is paramount. Movements are often slow, deliberate, patient. Predators wait, prey hide, and every encounter is shaped by the gamble of survival in dimness. For humans, the twilight zone offers both fascination and temptation. Its massive biomass of fish has drawn interest from commercial fisheries. Some companies see it as a new frontier for harvesting, a potential resource to feed growing populations. But scientists warn of caution. We know so little about the ecological role of these species that large-scale exploitation could collapse systems we do not yet understand. Removing vast numbers of lanternfish or bristlemouths might disrupt the carbon pump, alter predator-prey relationships, and send ripples through the entire ocean. The twilight zone is not just a reservoir of life. It is a linchpin in global stability. There is also the question of technology. Exploring the twilight zone pushes our equipment in subtle but difficult ways. Lights must be balanced to reveal without scaring. Cameras must be sensitive enough to capture faint glows. Vehicles must operate quietly so as not to disturb. Each expedition is a delicate dance between intrusion and observation. Too much presence, and we alter the very world we hope to study. Too little, and we see nothing at all. And yet, despite these challenges, the twilight zone captivates. It is neither day nor night, neither familiar nor alien. It is a realm of in-betweens, where creatures glow like stars in a liquid sky, where migrations happen on a planetary scale unseen, where giants drift silently and small fish number in the trillions. It is humbling to realize that right now, as you listen, billions of animals are rising through it, climbing silently toward the surface in the largest synchronized movement on Earth. Then, with dawn, they will fall again, disappearing back into dimness as they have for millions of years. The Twilight Zone reminds us that mystery doesn't always lie at the extremes. Sometimes it dwells in the middle, in the half-light where boundaries blur. To study it is to accept imperfection, to glimpse without fully understanding, to marvel at what little we can see while knowing there is far more hidden. It is not just strange life that lives there. It is strange life that defines it, life shaped by dimness, by scarcity, by the delicate balance between light and dark. And so, the journey continues, from twilight into deeper night, where light fades completely, and the creatures that remain are even stranger, even rarer, even more improbable than what we have seen so far. When you think of the deep sea, the first image that comes to mind is usually darkness. But the deeper you go, the more you discover something unexpected. Light. Not sunlight, not moonlight, but light made by life itself. This phenomenon is called bioluminescence, and it is one of the most extraordinary features of the deep. In a world where the sun never shines, countless creatures carry their own lanterns, glowing with colours and patterns that seem pulled from another reality. If pressure is the wall that guards the deep, and darkness is the blanket that covers it, then bioluminescence is the language that life has invented to speak within it. The first time you see it in person, it feels like magic. Divers who move through plankton-rich waters often describe trails of sparks following their hands as though they are swimming through stars. Ships cutting across the sea at night sometimes leave glowing wakes behind them, the churned water igniting with blue-green light. These displays come from tiny organisms, microscopic plankton that flash when disturbed. But in the depths, far below where any ship can pass, entire animals carry this glow as part of their bodies. Fish, squid, shrimp, jellyfish, many of them pulse with light from organs designed to produce it. At its core, bioluminescence is chemistry. Inside specialized cells or organs, molecules interact in reactions that release energy as light. The details vary among species, but the result is the same, a glow that can be turned on and off, sometimes in steady beams, sometimes in quick flashes. Unlike fire or electricity, bioluminescence produces almost no heat, making it efficient and safe for the creatures that rely on it. Evolution has used this tool in astonishingly diverse ways, giving rise to an entire vocabulary of light. Camouflage is one of the most common uses. In the Twilight Zone, faint light still filters down from above. Predators lurking below can see silhouettes against that glow. To counter this, many fish practice counter-illumination. They produce light on their undersides, matching the faint brightness from above so that their outlines vanish when seen from below. Imagine an airplane trying to hide from radar by projecting the exact image of the sky beneath its wings. That's what these fish are doing, but with light. Lanternfish, hatchetfish, and countless others have perfected this trick, disappearing into the half-light by carrying their own shadows. But light is not only for hiding, it is also for luring. The most famous example is the anglerfish, a predator with a glowing lure that dangles from a stalk above its head. In the pitch black of the midnight zone, that glow attracts curious prey. A small fish, thinking it sees something edible, swims closer, only to be swallowed by jaws lined with needle-like teeth. Some anglerfish even wave their lure in patterns, imitating the movements of small creatures, perfecting the deception. For them, light is not just a beacon, it is bait. Others use light to startle or escape. Certain shrimp and squid eject bursts of bioluminescent fluid, creating glowing clouds that confuse predators, much like an ink cloud. Some fish flash suddenly when attacked, startling their pursuers long enough to dart away. Others produce dazzling displays, waves of light that ripple across their bodies, making them harder to track. In a world without hiding places, light becomes both shield and distraction. Then there is communication. Many deep-sea species use specific patterns of flashes to signal to one another. Male and female firefly squid, for instance, coordinate with glowing patterns during mating. Some fish flash in unique rhythms, a kind of Morse code that identifies species or individuals. In the darkness, where colour and shape are useless for recognition, light becomes the script by which social lives are written. Entire conversations happen in bursts and pulses, invisible to human eyes, without special equipment. Some bioluminescence may even be used for hunting in ways we barely understand. Dragonfish, for example, produce red bioluminescent light. Most deep-sea creatures cannot see red, which disappears quickly with depth. To them, red light is invisible, but dragonfish have evolved special eyes sensitive to it. That means they can shine a light that only they can see, like a sniper using an infrared scope. They illuminate prey without being noticed, hunting under a secret spotlight. It is a trick that feels almost too clever, yet it is entirely natural. The colours of bioluminescence are also fascinating. Most of it is blue or green, the wavelengths that travel farthest in water. Blue penetrates deeper than red or yellow, so creatures using it can be seen over longer distances. But some species break this rule. Certain jellyfish glow with ultraviolet or violet light. Some squid produce golden or even pink flashes. And, as mentioned, dragonfish specialise in red. Each adaptation reflects an ecological strategy, shaped by who needs to see and who needs to remain unseen. The sheer abundance of bioluminescence is staggering. Some estimates suggest that more than 70% of deep-sea animals produce light in one way or another. Imagine walking into a forest where most plants and animals glowed faintly. That is what the deep sea is like, though instead of leaves and trunks, the light pulses in fish, jellies, worms and crustaceans. It is not empty darkness. It is a galaxy of living stars, blinking in patterns we're only beginning to decipher. For humans, these displays inspire awe, but they also inspire questions. How did such complex systems evolve? Why does light seem to be such a universal solution to the challenges of darkness? Scientists believe that bioluminescence evolved multiple times, independently, in different lineages. That suggests it is not an accident but a recurring answer to the problem of life without sunlight. When nature faces the challenge of darkness, one of its most reliable solutions is to make light. Bioluminescence is not confined to the deep sea, of course. Fireflies in summer fields, glowworms in caves, fungi that glow on decaying logs, all are examples of the same phenomenon. But nowhere is it as diverse, as essential, or as breathtaking as in the ocean depths. There, it is not an occasional quirk but the dominant visual language. Without it, life in the deep would be blind and mute. With it, life glows, communicates, hunts, hides, and thrives. There is also an eerie beauty to it. Footage of deep-sea expeditions often shows moments where, in the beam of a submersible's lights, a jellyfish pulses with glowing veins, or a swarm of tiny plankton flicker like embers in the dark. To watch is to feel as though you're gazing at fireworks slowed to a dreamlike pace. In those moments, the deep feels less like a place of fear and more like a place of wonder, an alien world where stars are not in the sky but in the water around you. And yet, we have only scratched the surface of understanding it. Many of the chemical pathways behind bioluminescence remain mysterious. Some organisms produce the chemicals themselves. Others rely on symbiotic bacteria that live within them, glowing in exchange for shelter and nutrients. The diversity of methods suggests that bioluminescence is not just one adaptation, but many, converging into the same outcome. If we could catalogue them all, we might uncover entirely new forms of chemistry, new insights into evolution, and even new tools for science and medicine. Already, bioluminescent proteins are used in laboratories as markers. helping researchers track genes, cells, and processes invisible to the naked eye. What was once only a curiosity has become a tool that drives discovery on land as well as at sea. For those who experience it firsthand, though, the scientific explanation often takes a backseat to the sheer spectacle. Imagine sitting in a submersible, lights turned off, drifting in silence thousands of meters below the surface. At first, there is nothing. Then, slowly, dots of light begin to appear. A fish with glowing spots passes by. A jelly drifts, its body shimmering in waves. A sudden flash bursts nearby as a startled shrimp releases a glowing cloud. For minutes at a time, it feels as though you are floating through space surrounded by stars. But these are not distant suns. They are living, breathing organisms, each with its own purpose for glowing. The effect is hypnotic, humbling, unforgettable. Bioluminescence also shapes how we think of the ocean culturally. Myths of glowing seas, legends of fiery waters, stories of lights beneath the waves, all reflect human encounters with these phenomena. Sailors in ancient times spoke of seas that glowed under their ships. Today, tourists visit bays where bioluminescent plankton light up with each paddle stroke. On a smaller scale, anyone who has swum in certain waters at night may have seen sparks trailing from their fingers, a private glimpse of the magic hidden in biology. In all these cases, what seems like fantasy is real, and what seems like a miracle is chemistry. The deep, however, amplifies it beyond imagination. There, light is not the background, but the exception. Each flash, each glow, each shimmer stands out against total darkness, a beacon in void. It is communication, deception, survival, and beauty rolled into one. It is life inventing its own stars because the sun no longer shines. As we drift further, we carry that image with us. Pressure may crush, darkness may conceal, but bioluminescence reminds us that life never stops finding ways to adapt, to flourish, to shine. In the deep ocean, where all seems impossible, life answers with light. And beyond this glowing realm, stranger still are the forms that evolve when size itself bends under the weight of the sea. One of the most curious things about the deep sea is how it seems to bend the rules of size. Some creatures down there are giants, far larger than their relatives near the surface, while others are so tiny and delicate that they seem like miniatures, as though carved in small scale. This pattern is called deep sea gigantism and dwarfism, and it is one of the strangest puzzles of evolution. In the vast, pressurized darkness, life takes on forms that defy our expectations, stretching and shrinking in ways that reveal how survival is written in shapes as much as in behaviors. Take the giant squid, perhaps the most famous of all. For centuries it was the stuff of legend, whispered about by sailors who swore they had seen monstrous tentacles rise from the deep. Today we know that colossal squid and giant squid do exist, and they are truly immense. Some individuals reach lengths longer than buses, their eyes the size of dinner plates, their tentacles armed with hooks and suckers. And yet, their relatives nearer the surface are much smaller. Something about the deep seems to encourage this kind of enlargement. Amphipods, small crustaceans that scuttle like shrimp, can grow to sizes 10 times greater in the abyss than their shallow water cousins. Even jellyfish reach extraordinary spans, with tentacles trailing longer than whales. Why does the deep create giants? Scientists have several theories. One is that the cold, high-pressure environment slows metabolism, allowing creatures to live longer and grow larger over time. Another is that in a place where food is scarce, being larger helps store energy and endure long periods without meals. Bigger bodies also move more efficiently in the vast distances of the deep, allowing animals to travel farther with less effort. In some cases, gigantism may even be a defense. A predator that can swallow a small fish may think twice when faced with a prey item many times larger than it expected. Whatever the reasons, the results are undeniable. The abyss is home to some of the largest invertebrates on Earth, At the same time, it is also home to some of the smallest. Tiny fish, no longer than a fingernail, drift in darkness. Delicate jellyfish, barely larger than raindrops, pulse slowly in the black water. Miniature snails and worms live on hydrothermal vents, their entire lives contained in spaces smaller than the palm of your hand. These small beings are not accidents. Just as gigantism has its advantages, so too does miniaturization. In a place where food is scarce, being tiny means needing less. Small creatures can survive on scraps, on particles drifting down as marine snow. They can hide in crevices, avoid predators, and reproduce quickly, ensuring survival even when the environment offers little. The coexistence of giants and miniatures in the same environment highlights the diversity of strategies evolution has taken. There is no single answer to survival in the deep. Some species gamble on size, growing huge to outlast hunger or intimidate threats. Others gamble on smallness, needing less and hiding more. The result is a surreal mix, where enormous squids drift alongside tiny glowing fish, where amphipods the size of cats share an ecosystem with creatures you could mistake for dust. For humans encountering these extremes, the impression is unforgettable. Submersible pilots describe the shock of seeing an amphipod the size of a loaf of bread, when they're used to seeing them no larger than a fingernail. Researchers pulling nets from the abyss sometimes find shrimp larger than their forearms, or worms that stretch far longer than they imagined possible. Then, in the same net, they may find creatures so fragile and small they disintegrate when touched. It is as if the deep sea is a place where scale itself has been loosened, where the normal rules of proportion no longer apply. Gigantism is not limited to squid and amphipods. Some isopods, relatives of the common pill bug that rolls into a ball on land, grow in the deep to the size of footballs. They crawl across the seafloor slowly, their armoured bodies looking almost prehistoric. Sea spiders, too, become enormous in polar and deep environments, their spindly legs stretching to lengths that make them look like nightmares from another age. Worms, sponges, and even single-celled organisms called xenophytophores grow to extraordinary sizes in the abyss, some of the latter reaching several centimetres across despite being just one cell. On land, single cells are microscopic. In the deep sea, a single cell can be large enough to cover the palm of your hand. Why does this matter? Because size influences everything about how life interacts. A giant amphipod can eat prey its shallow cousins could never dream of. A tiny fish can slip through nets and evade predators that would devour anything larger. The balance between giants and miniatures shapes the entire food web. Each adaptation is a response to the same conditions: darkness, cold, pressure, and scarcity. But the responses diverge wildly. In the deep, there is no one-size-fits-all solution. Humans often interpret gigantism as threatening, but in the ocean it is not always about aggression. Many of the giants are slow, fragile even. Giant squids, though enormous, are rarely aggressive toward anything but their prey. Giant isopods move sluggishly, scavenging rather than hunting. Even colossal jellyfish drift passively, their immense size less a weapon than an adaptation for gathering scarce food over large areas. The image of monsters lurking in the deep is more a reflection of our fears than of reality. More often, these giants are vulnerable in their own way, perfectly suited to their niche but fragile outside of it. On the other end, miniature creatures often go unnoticed, but they may be the true engines of the ecosystem. Their numbers are vast, their reproduction rapid, their role in recycling nutrients critical. Without them, the giants would have nothing to feed on. In this sense, the deep is a world of contrasts, where the massive and the minute depend on one another, each shaping the survival of the other. Culturally, the extremes of size in the deep have fueled imagination for centuries. Tales of krakens, of sea serpents, of monstrous creatures pulling ships under. These were often exaggerations of real encounters with large animals, glimpsed briefly in uncertain conditions. A whale entangled with a squid, a giant eel hauled in by accident, even shadows distorted by waves, these could become legends once retold. At the same time, the existence of countless tiny, unseen creatures in the water may have inspired myths of spirits, of unseen forces within the sea. Our ancestors sensed the extremes without fully understanding them, filling the gaps with stories. For modern science, the extremes are opportunities. Studying giant organisms reveals how biology can function under immense pressure. Studying miniature ones shows how life persists with minimal resources. Together they expand our understanding of the limits of life on Earth. They even offer clues about where life might exist beyond Earth. If creatures can grow immense or shrink tiny in the deep, perhaps life elsewhere in the universe might also play with scale in ways we cannot predict. The deep is not only Earth's frontier, it is a laboratory for imagining alien worlds. And then there is the sheer aesthetic strangeness of it. Imagine drifting in a submersible, lights casting a narrow beam into the black. Suddenly a giant squid appears, its tentacles stretching beyond the edges of your vision, its eye glowing faintly like a world unto itself. Then, just as suddenly, you notice tiny sparks, plankton flashing like fireflies, a fish no longer than your finger darting in and out of the light. Giants and miniatures together, coexisting in silence. The effect is surreal, unsettling and awe-inspiring all at once. It makes you realise that our sense of normal size is just a bias, shaped by the world we inhabit. On land, most animals fall within certain ranges, dictated by gravity, temperature, and available resources. In the deep, those rules are rewritten. Without light, with immense pressure, with scarce food, new shapes and sizes emerge. Normal does not exist. Only survival does, and perhaps that is the ultimate lesson of gigantism and dwarfism in the deep. Size is not about intimidation or beauty, or even efficiency alone. It is about adaptation. Whether a creature grows massive to endure hunger, or shrinks small to avoid notice, each choice reflects the endless creativity of evolution. The deep sea is not a place of uniformity. It is a place of extremes, and those extremes remind us that life will always find a way, even if that way looks strange to us. As we sink further, we carry with us the image of giants drifting like ghosts and miniatures flickering like sparks. They are the shapes survival has carved in the dark, and beyond them, the deep has even stranger languages still. Sounds that travel farther than sight, songs that echo through black water, voices carried not in light but in vibration. If sight is lost in the deep and light is scarce, another sense takes its place as the dominant language of the ocean, sound. The ocean is not silent, though it is often imagined that way. Beneath the waves, an entire world of vibrations, calls and echoes fills the water. Unlike light, which vanishes within a few hundred meters, sound travels extraordinarily well in water. In fact, it travels faster and farther there than in air. A sound made in the deep can sometimes be heard hundreds, even thousands of kilometers away. For life in the abyss, sound is not just background noise. It is how the world is mapped, how food is found, how dangers are avoided, and how communication bridges vast distances that vision cannot. For humans, this begins with wails. Few sounds are as haunting or as beautiful as the calls of a humpback, rising and falling in long melodic patterns. Whales are the great singers of the sea, and their songs can carry across oceans. Humpback songs are not random. They follow structures, repeating themes, and sometimes evolve over years, as if entire populations are slowly rewriting a shared melody. Other whales produce deep rumbles, whistles, or clicks. The blue whale, largest animal ever to live on Earth, produces calls so low in frequency that humans cannot hear them without special equipment. Yet those calls may travel thousands of kilometers, crossing entire basins. A single whale's voice can span oceans. For whales, These sounds serve many purposes: mating calls, social communication, even navigation. But they also reveal something profound about the medium itself. Sound is the one sense that can pierce the abyss. Where light fails and vision falters, sound remains. That is why not only whales but countless other creatures rely on it. Dolphins, though not deep dwellers, use echolocation, clicking and listening to the echoes to map their environment. Some deep-sea fish may use similar methods, though in ways less understood. Shrimp crackle, squid pulse, fish grunt and drum. The ocean is alive with sound, even when the surface above seems calm. Humans have learned this as well, often accidentally. During wartime, submarines relied on sonar, sending out pings of sound and listening for echoes to detect obstacles or enemies. Fishermen use sonar to locate schools of fish. Oceanographers use it to map the seafloor, bouncing signals off the bottom to build images of landscapes hidden beneath kilometers of water. Without sound, our knowledge of the ocean's shape would be almost non-existent. Where satellites map the moon with a light, we map the seafloor with sound. It is the only tool that can travel that far, that clearly through water. Yet sound in the deep is not only practical, it is cultural and emotional for us as well. The first time a person hears a whale call recorded from the abyss, there is often a sense of awe. The sound is low, resonant, haunting. It seems to come from everywhere at once, surrounding the listener. It is unlike any song on land, and it lingers in the imagination long after it fades. Some describe it as a voice from another world, and in a sense it is. These are voices shaped by the deep, designed to travel through black water where nothing else carries. But while sound allows connection, it also reveals the scale of the unknown. Scientists studying the deep have recorded noises they cannot identify, thumps, groans and hums that do not match any known creature or geological event. One of the most famous is the bloop, a low-frequency sound recorded in 1997 that was so loud it was detected across the Pacific Ocean. For years, speculation swirled that it could be a giant animal, perhaps something larger than any known whale. Later analysis suggested it was likely the sound of ice cracking in Antarctica, but the mystery lingered because it highlighted how little we know. Even today, the deep records noises we cannot fully explain. In a world where we assume everything has been catalogued, the ocean still whispers secrets in sound. For the animals themselves, sound is not just communication but survival. Predators may listen for the faint vibrations of prey. Prey may sense the drumming of a predator approaching. Many fish produce sounds by grinding teeth, vibrating muscles, or snapping body parts. The snapping shrimp, for instance, closes its claw so fast that it produces a shock wave and a loud pop, stunning small prey in the process. In some coastal waters, the collective snapping of shrimp is so loud that it drowns out other noises, creating a constant crackling that submariners have learned to recognize. In the open ocean, where the water is vast and empty, each sound becomes a signal, a marker, a thread of presence in the void. Sound also plays a role in navigation. Some deep-sea animals are thought to use the SOFAR channel, a layer of water at about 1,000 meters where sound travels particularly efficiently. Whales may dive into this layer to send their calls across oceans. Submarines have done the same, hiding their signals in the natural properties of the sea. This channel acts almost like a highway for sound, guiding voices across vast distances. In the darkness, it is as though the ocean has created its own invisible network of communication, a natural telephone line linking one end of the planet to the other. For humans, the dominance of sound in the deep presents both opportunity and challenge. On one hand, it allows us to study, map, and even communicate with the ocean. On the other, it means that our noise, ship engines, sonar, drilling, intrudes directly into the lives of marine animals. Increasingly, scientists warn of noise pollution in the sea. Whales that once communicated freely across basins may now be drowned out by the constant roar of shipping lanes. Sonar can disorient or even harm sensitive species. The ocean's natural soundscape is being altered by human activity, and the consequences ripple far beyond what we understand. The contrast between light and sound in the ocean is striking. Light is fleeting, fading quickly, limited to the near. Sound is enduring, stretching far, unbroken by darkness. To us who rely so heavily on sight, this reversal is humbling. It reminds us that our way of sensing the world is not universal. In the deep, vision is irrelevant, and sound reigns. For the creatures that live there, sound is not an accessory. It is life itself. Imagine being in a submersible, drifting with lights off in the midnight zone. You see nothing but blackness. Then you switch on hydrophones, and suddenly the silence is filled. You hear clicks, rumbles, pulses. Somewhere far away a whale calls, closer by a shrimp snaps. Perhaps a fish grunts, or water shifts as something large passes nearby. In an instant, the emptiness transforms into presence. You realize you're not alone. You're surrounded by voices, each speaking in its own way. The ocean, which seemed silent, is alive with sound. For us, this is a reminder that the world is always more than we perceive. In the ocean, we are nearly blind, but if we listen, we discover a symphony. Each click, each rumble, each call is part of a language we are only beginning to learn. For whales, that language is song. For fish, it may be pulses or grunts. For shrimp, it is snaps. For us, it is data, recordings, and curiosity. But beneath all of it lies the same truth. In the deep, sound is the bridge where sight cannot reach. And so, as we continue our descent, we leave behind the giants and miniatures of the abyss and follow the echoes deeper into regions where sound not only carries life, but reveals alien landscapes. Places where vents hiss, where tectonic plates groan, where the seafloor itself speaks in rumbles that shape the ocean above. The seafloor, for all its vastness, is not uniform. Much of it is flat abyssal plain, covered in sediment that drifts slowly downward over millennia. But scattered across this dark desert are places so dramatic, so alive, that they seem like something from another planet. These are the hydrothermal vents, towering chimneys of mineral and heat, often called black smokers. In the cold silence of the deep, they rise like alien factories, spewing clouds of hot, chemical-rich water into the sea. Around them, against all odds, life thrives. To understand why these vents exist, you have to think about the Earth itself. Beneath the seafloor, tectonic plates shift and grind. At mid-ocean ridges, the plates pull apart, exposing cracks through which seawater seeps deep into the crust. Down there, near magma chambers, the water heats to hundreds of degrees Celsius. It becomes infused with minerals, sulfur, and metals. When that superheated water finally gushes back into the ocean, it cools rapidly, and the minerals precipitate, building tall chimneys of black rock. These chimneys smoke with dark plumes, streams of particles so thick they look like underwater bonfires. The name Black Smoker comes from that appearance, though what rises is not smoke at all, but mineral-rich water. The first hydrothermal vents were discovered in 1977, and their discovery changed biology forever. Before then, scientists assumed all life on Earth ultimately depended on sunlight. Plants and algae captured it. Herbivores ate them. Carnivores ate herbivores, and so on. In the deep without sunlight, scientists assumed there could be only scattered scavengers feeding on the rain of particles from above. But when a team exploring the Galapagos Rift found hydrothermal vents, they also found thriving ecosystems clustered around them. Giant tube worms, clams, crabs, and strange fish lived in abundance where no light penetrated. It was a revelation. Life could exist without sunlight, powered instead by chemical energy from the Earth itself. At the centre of these ecosystems are chemosynthetic bacteria. Unlike photosynthetic organisms that use light, these microbes use chemicals like hydrogen sulfide, abundant in vent water, as their energy source. They oxidize the sulfide and harness the energy to build organic molecules, just as plants do with sunlight. These bacteria live freely in the vent water, coating rocks and surfaces. But they also form symbiotic relationships with larger animals. Giant tube worms, for instance, have no mouth or digestive system. Instead, they host chemosynthetic bacteria inside their bodies, providing them with chemicals from the vent water and receiving nutrients in return. The worms can grow several meters long, their white tubes topped with blood-red plumes that wave in the dark like alien flowers. The discovery of these organisms reshaped not only our view of the deep sea, but our view of life itself. If life could exist without sunlight, powered only by chemistry, then perhaps it could exist in similar environments elsewhere, on icy moons like Europa or Enceladus, where liquid oceans may lie beneath frozen crusts, warmed by hydrothermal activity. The vents on Earth became analogues for alien ecosystems, clues that life might be more universal than we thought. The communities around hydrothermal vents are astonishingly diverse. Giant clams with shells bigger than dinner plates cluster around the chimneys, their flesh sustained by symbiotic bacteria. Crabs and shrimp crawl across the rocks, grazing on bacterial mats. Certain shrimp species are nearly transparent, their bodies glowing faintly from the heat. Fish hover nearby, opportunistic hunters in the midst of abundance. Even microorganisms form vast colonies, painting the rocks with colours that range from orange to black to white. In an otherwise barren seafloor, vents are oases, bursts of life in the middle of emptiness. Yet these oases are fragile and transient. Hydrothermal vents do not last forever. Chimneys collapse, cracks shift, flows move. A vent may thrive for decades or centuries, then suddenly die as the geology changes. When that happens, the communities around it must either adapt, move, or perish. The cycle of creation and destruction is constant, shaping a world in which survival depends on flexibility. To us it seems cruel. To the organisms there it is simply reality. The vents also challenge our notions of temperature. The surrounding ocean, just a few meters away, hovers near freezing. The vent fluid, emerging from the crust, may exceed 350 degrees Celsius. Between these extremes, gradients form, and life positions itself precisely where survival is possible. Tube worms thrive in the warmth, but not too close to the scalding jet. Shrimp cluster in zones where heat is tolerable, but food is abundant. It is a delicate balance, a dance between fire and ice, invisible without instruments but vital to every creature there. For humans encountering these places, the impression is profound. Submersibles descending into the darkness may travel for hours through barren plains, then suddenly stumble upon towering chimneys belching black plumes, surrounded by forests of tube worms. The scene looks alien, surreal, and yet it is Earth. Pilots often describe it as stepping into another world entirely, and in a sense it is. These vents are as different from the surface as deserts are from forests, as mountains are from swamps. They are entire ecosystems unto themselves, stitched to the planet's geology rather than the sun. There are also variations beyond black smokers. White smokers, for instance, emit cooler water rich in different minerals, building chimneys coated with lighter deposits. These can host different microbial communities and attract different animals. Alkaline vents, such as the Lost City hydrothermal field discovered in the Atlantic, spew fluids rich in hydrogen and methane, creating towering carbonate structures that look like spires and cathedrals under the sea. These vents are particularly intriguing to scientists studying the origin of life, because the chemistry they produce resembles the conditions that may have given rise to the first cells on Earth. In their porous walls and chemical gradients, some researchers see a plausible cradle for biology itself. Hydrothermal vents also remind us of the deep sea's wealth and fragility. The minerals they emit include valuable metals like copper, zinc, and gold. Mining companies have expressed interest in exploiting these resources, sending robotic harvesters to scrape chimneys and collect deposits. But scientists warn that such activities could devastate ecosystems before we even understand them. Vents are rare, scattered, and crucial to unique species found nowhere else. Disturbing them risks erasing entire worlds of life in the pursuit of short-term gain. Once destroyed, they may never recover. For science, the vents are invaluable. They teach us about the adaptability of life, the chemistry of Earth's interior, the cycles of the ocean, and the possibilities of existence beyond our planet. For imagination, they are equally powerful. To look at a vent field glowing faintly in submersible lights, swarming with bizarre creatures, is to glimpse what truly alien ecosystems might look like elsewhere in the universe. It is to see proof that life does not need the sun, only energy, water, and the right chemistry. Culturally too, they resonate. The idea of fire under the sea has appeared in myths for centuries. Volcanoes beneath the waves, underworlds hidden below. Hydrothermal vents bring that imagery to life. They are literal places where fire and water meet, where Earth's molten interior touches the ocean's frozen silence. No wonder they feel otherworldly. They are reminders that beneath the surface lies a planet still alive, still changing, still shaping its own biospheres in ways we barely comprehend. The vents are not isolated curiosities. They are part of a global system, linked to tectonic activity, spreading ridges, and volcanic processes that drive the shape of Earth itself. Without them, the ocean's chemistry would be different. Without them, perhaps life itself would never have begun. Every puff of mineral-rich water, every chimney, every colony of bacteria is a thread in a story that stretches back to the origin of the planet. And each one still shapes the present, quietly, invisibly, in the depths we rarely see. Imagine sitting in a submersible, lights illuminating a vent field. Towering chimneys loom in the darkness, some 10 meters tall, shimmering with heat. Around them, clouds of black particles billow upward, twisting into the water like smoke in air. Tube worms wave gently, their red plumes vivid against the gloom. Crabs scuttle, shrimp swarm, fish hover, bacteria coat every surface. The water is alive with movement, a stark contrast to the empty plain surrounding it. You realize you are witnessing a miracle of survival, a pocket of abundance in a world of scarcity. And then it hits you. This isn't science fiction. This is Earth, right now, hidden beneath miles of water, thriving unseen. These alien worlds remind us that the deep is not uniform emptiness. It is patterned, diverse, filled with surprises. Pressure and darkness may dominate, but within them, geology and chemistry carve out habitats as rich as any forest or desert. The black smokers are just one example, but they show us how astonishingly creative nature can be when given the right conditions. And as we drift away from the glowing chimneys, deeper still into the abyss, we follow not the light of the sun but the chemical fire of the earth, guiding us toward the next mystery, life that survives not on photosynthesis, but on chemosynthesis, rewriting the very rules of what it means to be alive. If you were to ask someone how life survives on Earth, the answer you would almost always hear is sunlight. Plants capture it, algae soak it in, and through photosynthesis, the energy of the sun becomes the foundation of nearly every food chain. Everything we eat, directly or indirectly, traces back to that conversion of light into sugar. Grass feeds cows, trees bear fruit, algae sustain plankton, and all of it begins with photosynthesis. Without sunlight, the assumption has long been that life would collapse, but the deep sea teaches us otherwise. There, far below where the last ray of light can penetrate, entire ecosystems exist without the sun. They are not barren wastelands or desperate scraps of scavengers. They are lush, thriving, crowded communities clustered around chemical energy instead of light. The process that fuels them is called chemosynthesis. and it is one of the most revolutionary discoveries in biology because it shows that life can flourish even in places where the sun will never shine. Chemosynthesis, in essence, is the use of chemical reactions to build organic matter. Instead of harnessing photons, chemosynthetic microbes use energy from molecules like hydrogen sulfide, methane, or hydrogen. In hydrothermal vent communities, for example, bacteria oxidize hydrogen sulfide from the vent water. The energy released in that reaction is used to fix carbon dioxide into sugars, just as photosynthesis does with light. Those sugars become the base of a food web. From that single reaction flows the energy that sustains tube worms, crabs, clams, shrimp, and fish. Where photosynthesis is a bridge from sunlight to life, chemosynthesis is a bridge from geology to life. The discovery of chemosynthesis-driven ecosystems in 1977 was a shock to science. Before then, biologists assumed the deep was sustained only by the marine snow falling from above, bits of organic matter drifting downward over months. And while that rain of particles does feed much of the deep, the vents showed something entirely new, life that does not rely at all on the surface. These communities are completely independent of the sun. Their energy comes directly from Earth's interior. That independence reshaped how we think of the planet. It suggested that life is not bound to the sky, but could emerge wherever the right chemistry occurs. Consider the tube worms that grow around black smokers. They're astonishing creatures, sometimes several meters long, anchored in white tubes. They have no mouths, no stomachs, no digestive systems at all. Instead, their bodies house dense colonies of bacteria that perform chemosynthesis. The worms absorb sulfide and carbon dioxide from the water, provide them to the bacteria, and in return receive nutrients. It is a partnership so complete that the worms are entirely dependent on their microbes, and the microbes are entirely dependent on the worms. Together, they thrive in an environment that would be lethal to most life. Other creatures follow similar strategies. Clams at vents host chemosynthetic bacteria in their gills, feeding not on plankton but on the products of chemistry. Mussels, crabs, even certain shrimp species do the same. In some cases, animals graze directly on bacterial mats coating rocks around vents. In others, they filter free-living microbes from the water. The entire food web begins not with sunlight, but with sulfide, methane, and other chemicals rising from the earth. What makes this even more fascinating is how diverse the chemosynthetic pathways are. Some microbes oxidize sulfide, others methane, others hydrogen. Some live in scalding hot vent fluids, others in cold seeps where methane leaks slowly from sediments. Each niche provides its own chemistry, and microbes evolve to match. Around them, larger animals adapt in turn. The result is a patchwork of ecosystems, each distinct, each sustained by the chemistry of its location. Cold seeps, for instance, are places where hydrocarbons ooze from the sea floor. They're quieter than vents, cooler, but just as rich in life. There, chemosynthetic bacteria use methane as their energy source, supporting mussel beds, clam colonies, and tube worms different from those at hot vents. Whale falls, carcasses of whales that sink to the bottom, also become sites for chemosynthetic life. As the whale's bones decompose, they release sulfides, which bacteria exploit, forming yet another temporary ecosystem. Again and again, wherever chemicals seep from rock into water, chemosynthesis takes root. For science, the implications are immense. If life can exist without sunlight here, it might exist elsewhere under similar conditions. Moons like Europa and Enceladus, with their subsurface oceans warmed by geological activity, may host hydrothermal vents of their own. Mars, once volcanically active, may have had places where chemosynthesis could occur. The principle is universal. Life needs energy, water, and carbon. If energy can come from chemistry instead of light, the possibilities expand enormously. Suddenly, the universe looks more hospitable. But chemosynthesis is not just about possibility, it is about resilience. The Earth itself has endured cataclysms, asteroid impacts, volcanic winters, ice ages. Each time, surface life may have faltered, but deep below, chemosynthetic communities would have continued largely unchanged. They are buffered from the surface. The sun could vanish, and vents would keep flowing. In this sense, chemosynthetic life is a reminder of how robust life can be. It doesn't cling only to fragile chains of light. It digs into the rock itself, drawing energy from the planet's furnace. For humans, encountering these communities is humbling. Pilots describe the surreal sight of a vent field swarming with giant clams, crabs, and worms. In the darkness, these organisms live abundantly, not scavenging scraps but thriving in their own right. It feels like stumbling upon an alien city, hidden in the dark, powered by forces you didn't know could sustain life. The effect is not only scientific but emotional, a reminder that our assumptions about what is necessary are often too narrow, and the adaptations here are not just functional, they are beautiful in their strangeness. Tube worms with their blood-red plumes waving in the vent currents, clams clustered like shining coins around chimneys, shrimp with glowing backsides huddling near hot fluid, bacterial mats painting rocks with orange and white. To us they look bizarre, alien. To themselves, they are simply home. The concept of chemosynthesis also raises questions about the origin of life. Some scientists believe that early Earth, more than 3 billion years ago, may have hosted alkaline hydrothermal vents with chemistry similar to what we see today. In those vents, natural gradients of pH and temperature could have driven the formation of complex organic molecules. The porous rocks would have provided shelter, the flows of minerals would have provided energy. Perhaps life began not in sunlight at the surface, but in chemical fire beneath the sea. If true, then the story of life on Earth starts in darkness, not light. It's worth imagining what that means. When we look at the green of plants, the forests, the crops, we think of them as the essence of life, but deep below, long before forests ever grew, life may have been microbial colonies clinging to vents, drawing power from sulfide and methane. In that sense, chemosynthesis is not a strange exception. It may be the original path. Photosynthesis could be the later adaptation, expanding life into the sunlight once it became available. If so, the deep sea does not just hold alien worlds, it holds echoes of our own beginning. Even today, chemosynthetic communities are not rare anomalies. They are widespread, from the hot smokers of the Pacific to the cold seeps of the Gulf of Mexico, from whale falls off the coast of California to methane hydrates in the Arctic. They remind us that Earth is more dynamic, more inventive than our surface-centered perspective allows. But they are also fragile. Hydrothermal vents and cold seeps are easily disturbed. Mining for metals, drilling for oil and gas, or even careless exploration could wipe out unique communities. Because they exist far from the public eye, their protection is often overlooked. Yet their importance, both scientifically and ecologically, is enormous. Preserving them means preserving not just ecosystems, but insights into the very nature of life. For those who drift among them, the impression lingers. To see life without sunlight is to realize that the boundaries we imagine are illusions. Life does not need our rules. It needs only opportunity. And in the deep sea, opportunity comes not from the sky but from the earth itself, rising in plumes of hot water, in seeping flows of methane, in the quiet release of sulfides from rock. And as we leave these oases of chemistry, the story does not end. Beyond them lie creatures that stirred our oldest myths, animals so large and elusive that they haunted sailors' imaginations for centuries. The next mystery is not just about survival in chemistry, but about how our stories and legends meet the reality of the deep. For as long as humans have sailed across oceans, they have told stories of monsters lurking beneath the waves. When the sea was unknown, when navigation meant trusting stars and winds across horizons that seemed endless, it was natural to imagine that the darkness below held creatures capable of swallowing ships whole. These legends passed from sailor to sailor, from culture to culture, growing with each retelling. Some were warnings, others were entertainment, but many were born from glimpses of real animals that surfaced just long enough to spark awe and fear. In the deep, where strange forms truly do exist, myth and reality overlap more than we like to admit. Among the most famous of these creatures is the kraken, a legendary beast said to dwell off the coast of Norway and Greenland. Sailors spoke of a monster so vast it could wrap its tentacles around an entire vessel, pulling it beneath the waves. Some descriptions painted it as more like an island than an animal, its bulk so immense that ships anchored to it, mistaking its body for land. Tales of the kraken spread through Europe in the 17th and 18th centuries, becoming symbols of the terror and mystery of the sea. And yet, behind those exaggerated accounts lies something real: the giant squid. For centuries, the giant squid was only speculation. Fishermen occasionally hauled up pieces of tentacle, carcasses washed ashore, or scars on whales that hinted at titanic battles. But living specimens remained unseen. This fueled the legend, allowing imagination to fill the void. It was not until the early 21st century that scientists finally captured images of a giant squid in its natural habitat. What they found was no less astonishing than the myths. These animals can grow more than 10 meters long, their eyes among the largest of any creature on Earth, perfectly adapted to detect faint glows in the darkness. Their tentacles are lined with powerful suckers, some with serrated rings capable of tearing into prey, or into the flesh of a whale. Even larger, perhaps, is the colossal squid, found in the Southern Ocean around Antarctica. Though less well known than its cousin, it rivals or even exceeds the giant squid in mass. Its tentacles are equipped not only with suckers, but with rotating hooks, and its eyes are so large they can detect faint shadows, even in the midnight depths. Very few have been observed, but the evidence we have suggests a creature every bit as formidable as the legends implied. Encounters between these squids and sperm whales add further fuel to the stories. Sperm whales dive deep, often more than a kilometre, to hunt squid. They bear scars on their heads, circular marks left by giant suckers. These scars are evidence of battles in the dark, titanic struggles between massive predators and enormous prey. Sailors who encountered dead whales bearing these wounds could hardly be blamed for imagining monsters large enough to fight whales head-on. The kraken may be a myth, but the giant squid is proof that the ocean truly does harbour animals of monstrous scale. And it isn't just squid. Many other creatures of the deep inspired myths. Oarfish, for example, a long ribbon-like fish that can grow more than 10 metres. They live in the mesopelagic zone but occasionally surface, especially when sick or dying. To sailors, seeing a shimmering silver serpent-like fish writhing at the surface could only mean one thing: sea serpent. Oarfish sightings likely contributed to countless stories of massive snakes lurking in the water. Their elongated bodies, undulating motion, and sudden appearances near coasts would have been unforgettable for anyone unfamiliar with them. Sharks, too, played their part. The Greenland shark, living in Arctic depths, is massive, slow, and ancient, some individuals estimated to be hundreds of years old. Imagine catching sight of a sluggish, enormous shark in freezing waters centuries ago. It could easily be mistaken for a mythical monster, an ancient guardian of the sea. Basking sharks, which feed on plankton, sometimes wash ashore decomposed, their bodies distorted in ways that make them look like sea dragons or serpents. Early reports of monsters often came from such carcasses, misinterpreted by frightened or awestruck observers. Then there are the anglerfish, with their grotesque jaws and glowing lures. For most of history, no one knew they existed, but fishermen pulling up strange, deformed fish from the depths sometimes found specimens that looked terrifying. With fanged mouths, distended bodies, and bioluminescent organs, they could have easily inspired tales of demons from the sea. The gulper eel, with its enormous mouth capable of swallowing prey larger than itself, might also have sparked myths of bottomless maws waiting below. The overlap between myth and reality is what makes these stories so enduring. They are not just fabrications, but interpretations of encounters with real animals filtered through fear, wonder, and imagination. For sailors far from land, weeks into voyages, often exhausted and superstitious, it didn't take much for a sighting to become a legend. And in truth, the ocean encourages such thinking. Its vastness, its unpredictability, its darkness, all make it a natural stage for monsters. Even today, the idea of sea monsters lingers in popular culture. From literature like Moby Dick and 20,000 Leagues Under the Sea, to films that imagine colossal beasts rising from the depths, the ocean remains fertile ground for our fears and fantasies, and why not? Unlike land, where nearly every corner has been mapped, the ocean still holds real mysteries. Knowing that giant squid exist only makes the legends of the Kraken more compelling. Knowing that creatures with hooks, lights and jaws actually drift in the abyss makes the idea of monsters feel less like fantasy and more like possibility. Science, of course, strips away exaggeration, but it also reveals wonders of its own. The giant squid is no less impressive for being real. The colossal squid, the oarfish, the deep sharks, these are creatures of staggering scale and strangeness. They show us that our ancestors were not entirely wrong to imagine monsters in the deep. They simply lacked the knowledge to explain what they saw, and perhaps in their fear, they captured a truth we still feel. The deep is a place where our control falters, where other beings rule, where size and power belong not to us but to creatures adapted to darkness. But it is also worth noting that the word monster reflects our perspective, not theirs. To a squid, to an oarfish, to a shark, they are not monsters at all. They are simply life shaped by the pressures and scarcities of the deep. Their size, their strangeness, their adaptations, they are all logical solutions to survival in an alien environment. What seems monstrous to us is natural to them. It is our imagination that paints them as horrors. Still, the resonance of these myths tells us something about ourselves. The sea represents the unknown, and in the unknown we place our fears. The Kraken was not just a story about squid. It was a story about helplessness, about human fragility in the face of nature's vastness. The sea serpent was not just an oarfish. It was the embodiment of uncertainty, the idea that beneath the waves might lurk forces beyond our comprehension. Even today, with satellites and submersibles, those feelings linger. To gaze at the ocean is still to wonder what lies beneath, and in some sense, that wonder is justified. Because even with modern science, we continue to find creatures that surprise us. The monsters of the deep are not confined to legend. They are real, though often stranger than myth described. Each expedition brings back footage or specimens that challenge what we thought possible. A jellyfish pulsing with lights like a chandelier, a squid with arms longer than cars, a fish with jaws that unhinge like nightmares. The sea remains a place where monsters exist, not as demons, but as marvels. So the next time you hear of the Kraken, the sea serpent, the Leviathan, remember that those myths are not simply fantasies. They're echoes of real encounters with creatures of the deep. The monsters of our stories are reflections of the monsters of the ocean, which are not monsters at all, but survivors of an environment we barely understand. And as we descend further, we leave behind the legends and step into the practical barriers that have kept these realities hidden. Barriers of technology, cost, and human limitation that explain why, even now, so much of the deep remains unknown. Exploring the deep sea is not a matter of simply diving in. The obstacles are immense, and at every stage, technology is the deciding factor. Unlike the surface of the earth, which we can walk, or the sky, which we can fly, the ocean places limits on our bodies almost immediately. Beyond a few dozen meters, lungs struggle. Beyond a few hundred, bones and blood face pressures they cannot withstand. To go farther requires machines, and those machines must fight against conditions as hostile as space. The story of deep-sea exploration is not just about curiosity, It is about engineering, invention, and the constant battle with limitations that seem designed to hold us back. Submarines were the first tools that allowed humans to go beyond what diving alone could achieve. Early designs were crude, small vessels with thick hulls, little maneuverability, and almost no view. But even those crude beginnings proved that humans could, at least in theory, descend where no sunlight reached. Over time, designs improved, hulls grew stronger, and propulsion more efficient. By the 20th century, submersibles were being built specifically for research, equipped with portholes, robotic arms, and instruments to sample water, rock, and life. One of the most famous of these was the bathyscaphe Trieste, which in 1960 carried Jacques Piccard and Don Walsh to the bottom of the Mariana Trench. Their descent to nearly 11 kilometres was a milestone, the first time humans reached the deepest known point on Earth. The Trieste was essentially a steel sphere attached to a float filled with gasoline for buoyancy. It had no lights strong enough to see much, no cameras of high quality, and the dive was brief. But it proved that human technology could withstand pressures greater than 1,000 times what we feel at the surface. For decades afterward, few followed. The cost, the risk, and the difficulty were simply too great. Later, in the latter half of the 20th century, submersibles like Alvin brought exploration to new heights. Alvin, operated by the United States, made thousands of dives, including the discovery of hydrothermal vents in 1977 and the exploration of the Titanic wreck in 1985. Its ability to carry scientists directly into the deep, with lights, cameras, and manipulator arms, made it a workhorse of oceanography. Other countries developed similar vehicles, from Japan's Shinkai to France's Nautil. Each expanded our reach, letting us see more, collect more, and understand more. Yet each also highlighted the limitations. Dives are expensive, lasting only hours. The area that can be explored on a single dive is tiny compared to the scale of the ocean. Every submersible is a small bubble of air in an endless desert of water. Because of these limits, remotely operated vehicles, or ROVs, became essential. ROVs are unmanned, tethered to ships by cables that transmit power and data. They can descend deeper than manned submersibles, stay longer, and take greater risks. Some are small, the size of a suitcase, while others are large enough to carry multiple robotic arms and heavy tools. They film, sample, and manipulate with precision, controlled from the surface by teams of operators. Famous ROVs like Jason, Victor, and Kaiko have mapped trenches, filmed bizarre life, and even laid the groundwork for undersea infrastructure. Their advantage is safety. No human is inside, so if they fail, no life is lost. Yet ROVs have their own constraints. Their tethering cables, sometimes kilometres long, are prone to tangling, damage, or drag. Their range is limited by the ship above. Storms or surface conditions can halt operations even if the deep itself is calm, and the cost remains high. Every ROV requires a specialised ship, trained crew, and maintenance. Deploying one is a major operation, not something done casually. In recent years, autonomous underwater vehicles, or AUVs, have added a new dimension. Unlike ROVs, AUVs are not tethered. They are programmed before launch to follow specific paths, collecting data with sonar, cameras, and sensors, then return to the surface. This freedom allows them to cover broader areas, mapping seafloors with unprecedented detail. Some can travel hundreds of kilometres on a single mission. AUVs have revolutionised the mapping of trenches, ridges, and even shipwrecks. But autonomy brings risks too. Without a tether, real-time control is impossible. If an AUV fails or is lost, recovery may never happen. The ocean swallows machines as easily as it swallows anything else. All of this underscores a single truth. Exploring the deep sea is expensive and fragile. Space exploration often garners headlines and budgets in the billions. Ocean exploration, by comparison, is funded sparsely, with fewer resources and less attention. Yet the technological challenges are no less daunting. In some ways, They are greater. Space is empty, a vacuum. The deep sea is heavy, crushing, corrosive. Machines must not only endure pressure but function in near-freezing water, total darkness, and shifting currents. Cameras fog, lights break, electronics short. Every dive is a gamble, every mission a test of endurance. The limitations extend beyond the machines themselves. Communication underwater is a fundamental problem. Radio waves, the backbone of modern technology, do not travel well in seawater. Satellites cannot reach below the surface. Submersibles and ROVs rely on cables or on low-frequency acoustic signals that transmit slowly and with limited bandwidth. In practice, this means deep-sea exploration is almost always slow, cumbersome, and delayed. Operators cannot live stream with the same immediacy they would on land or in space. Instead, they interpret grainy video, delayed signals, and narrow data streams, piecing together the world in fragments. Visibility is another challenge. Water scatters and absorbs light, and the deeper you go, the worse it gets. Submersibles must carry massive lamps to see even a few meters ahead. But too much light can scare animals, changing their behavior. Too little, and nothing is visible at all. Cameras must be carefully calibrated, sensors carefully placed, every detail balanced between intrusion and observation. What we capture on film is never the whole truth of the environment. It is always filtered, distorted, partial. Then there is cost. Building a research submersible can take decades and tens of millions of dollars. Operating it requires ships, crews, fuel, and logistics that stretch budgets thin. A single dive can cost more than most people make in a year. This is why so few countries maintain active programs. A handful of vehicles do most of the world's deep-sea exploration. Compared to the size of the ocean, their reach is microscopic. We often say we know more about the surface of Mars than the seafloor of Earth, and the reason is not just difficulty. It is priority. We choose to spend more on the stars than on the abyss beneath our feet. Despite all this, progress continues. New materials make hulls lighter and stronger. Better batteries extend the range of AUVs. High-definition cameras and improved sensors bring clarity where once there was only blur. Projects like Seabed 2030 aim to map the entire ocean floor in detail by the end of this decade, relying on fleets of AUVs and sonar-equipped ships. Private initiatives, too, are pushing boundaries, from billionaire-funded submersibles to commercial expeditions. Yet each success also highlights how much remains undone. The ocean is vast and our machines are small. Every dive shows wonders, but also reveals how little we have touched. Perhaps the most striking limitation is human presence itself. Only a handful of people have ever been to the deepest parts of the ocean. Far more have been into space than into the Challenger Deep. The reason is not only pressure, but the fragility of life in such an environment. Human bodies need air, warmth, food, and safety. Machines need only power and structure. As a result, much of what we know about the deep comes from machines alone, not from direct human experience. The sense of presence, of seeing with our own eyes, is rare. That rarity adds to the mystery, keeping the deep at arm's length, even as we explore it. And so, the story of deep-sea exploration is one of struggle. Submarines give us access, but only in brief glimpses. ROVs extend our reach but tether us to the surface. AUs expand coverage but risk loss and failure. Each technology is a tool, each with strengths and weaknesses. Together, they form our current arsenal against the abyss. But against the scale of the ocean, they are still fragile, still limited. Yet it is precisely these struggles that make each discovery meaningful. To see a giant squid alive, to film tube worms waving in vent currents, to map trenches deeper than Everest is tall, each achievement comes not easily, but against resistance. The ocean demands effort, ingenuity, and patience. It gives nothing freely. And maybe that is why it still inspires us. The struggle makes the mystery deeper, the discoveries sweeter, the journey more humbling. As we press on past the limits of our machines and the fragility of our efforts, another question rises. Why, with so much left to uncover, do we so rarely choose to explore? The answer is not only technical, it is also about cost, risk, and the priorities of humanity itself. When people hear that more than 80% of the ocean is still unmapped, unexplored, and unseen by human eyes, the reaction is often disbelief. How could it be, in an age of satellites, space telescopes, and rovers on Mars, that the very surface of our own planet remains so hidden? The truth is that exploring the deep ocean has never been as common or as prioritized as exploring space. It is not because the technology is impossible. We've proven that we can dive, map, and study. The real reasons lie in cost, in risk, and in the way humanity chooses its priorities. The ocean is vast, covering more than 70% of Earth's surface. That alone makes it daunting. To map and explore it fully would require countless missions, fleets of ships, decades of continuous effort. Each expedition is expensive, demanding specialized vessels, submersibles, or remotely operated vehicles, scientific crews, engineers, and logistics. A single day at sea with a research vessel can cost tens of thousands of dollars. A single deep-sea dive can cost more than some entire terrestrial field studies. Compared to sending a satellite into orbit, the price per area explored is often far higher. This financial reality makes every mission a negotiation. Grants are limited, governments have other priorities, and research teams compete for scarce resources. Risk compounds the cost. Unlike satellites, which can fail silently in orbit without endangering lives, deep-sea exploration often involves humans and machines in environments where failure means instant destruction. Pressure at the bottom of the Mariana Trench is so great that even a small flaw in a submersible's hull could be catastrophic. ROVs and AUVs face their own dangers, tether cables snapping, electronics failing, machines lost forever in the abyss. Each risk represents not only financial loss, but years of planning gone in a moment. Scientists and funders alike must weigh whether the knowledge gained justifies the danger. Often the answer is hesitation. Then there is perception. Space exploration carries glamour. Images of astronauts floating weightless, of rockets launching into the sky, of distant planets revealed in photographs. These inspire the imagination. Governments see space as a stage for prestige, a way to demonstrate power, innovation, and leadership. The moon landing was not only a scientific achievement but a geopolitical one, a symbol of national pride. The ocean, by contrast, is harder to romanticize. A grainy video of strange fish or vents does not ignite the same excitement as a rover on Mars. Ships sinking in black water do not carry the same heroic narrative as astronauts planting flags on new worlds. In short, space has better publicity. The abyss remains in shadow. Public perception shapes funding, and funding shapes exploration. Most nations devote a fraction of their research budgets to oceanography compared to aerospace. Universities and private companies often follow the same trend. Even when the ocean directly affects climate, weather, and food security, its mysteries remain less politically urgent than the allure of the stars. The irony is striking. We depend on the ocean daily, but we dream of other planets nightly. Another factor is accessibility. Space is distant but simple in its uniformity. Once you leave Earth, there is vacuum. The rules are constant. The deep sea, however, is unpredictable. Storms at the surface can halt missions. Currents twist cables. Temperatures shift. Sediment clouds cameras. Life is fragile, so instruments must avoid too much disturbance. Every expedition is a battle not just against depth, but against complexity. The variability makes results slower, harder to control, and sometimes less dramatic. That slowness does not appeal to those looking for quick breakthroughs or spectacular images. And then there are economic interests. Much of space exploration promises future industries, satellite networks, asteroid mining, colonization. Investors can see the potential profits, however distant. The deep ocean does have resources, minerals at hydrothermal vents, oil and gas reserves, fisheries, but accessing them is difficult and controversial. Mining vents risks destroying unique ecosystems. Overfishing depletes stocks faster than they can recover. Drilling carries hazards of spills and disasters. The profit exists, but it comes entangled with risk and environmental costs. For governments and corporations, the ocean can look less like opportunity and more like liability. The human element also plays a role. For scientists, the allure of the unknown is always there, but exploration requires sacrifice. Months at sea, away from home, working in cramped quarters on research vessels, dealing with unpredictable weather and the monotony of long waits. Missions can be exhilarating, but they can also be grueling. Not every scientist chooses the sea when other fields offer laboratories on land, easier schedules, and more predictable careers. The ocean demands not only money and technology, but people willing to endure the hardships of working at its edge. Yet none of these barriers are absolute. They are choices. The technology exists. The ability exists. What is missing is willpower. When humanity has chosen to prioritize something, space exploration, nuclear power, medical research, we have poured resources into it and achieved extraordinary results. The lack of similar commitment to ocean exploration reveals something about our values. We chase what we can see, what captures attention, what elevates national pride. The ocean does not fit neatly into those categories, so it waits, unexplored, even as its importance looms over us. It is worth pausing on the irony. The ocean regulates climate, provides food for billions, cycles carbon, and generates most of the oxygen we breathe. It is our planet's life support system. Yet we devote more money and attention to distant planets than to the seas that keep us alive. The argument that we must first know Earth before we leave it is often repeated, yet rarely acted upon. Instead, we live in a paradox, dreaming of colonizing Mars while barely understanding the abyssal plains beneath our own world. Part of the problem is visibility. People see rockets launch. They do not see sonar surveys or submersible dives. They feel connected to astronauts, but not to marine biologists drifting in dark ships far offshore. To many, the ocean feels abstract, a backdrop to beaches and coastlines rather than a frontier. That perception has consequences. Funding follows visibility, and visibility follows spectacle. Without spectacle, the ocean remains overlooked. There is also fear. The sea inspires awe, but also dread. For every story of discovery, there are stories of shipwrecks, storms, and disappearances. To the public, the ocean feels less like a destination and more like a hazard. That fear makes it harder to embrace exploration. It is easier to romanticize astronauts floating gently in orbit than divers being crushed under pressure. Our psychology gravitates toward the uplifting, not the crushing. And yet, despite all these reasons, exploration does continue. Dedicated teams, often working with limited resources, map seafloors, study vents, tag animals, and record sounds. They reveal wonders at every step. Each discovery shows not only what is possible, but what is missed by neglect. Every new fish, every new ecosystem, every new geological feature reminds us how incomplete our picture is. If we chose to prioritize the ocean with the same urgency as space, the returns could be staggering, not only in knowledge, but in medicine, technology, and even inspiration. The rarity of exploration is not permanent. Technology grows cheaper, more autonomous, more widespread. Fleets of AUVs may one day map the seafloor continuously. Satellites may refine methods to infer detail indirectly. Collaboration between nations may expand efforts. But whether we seize those opportunities depends on choice, not fate. We can treat the ocean as background or as frontier. We can keep it hidden or bring it into focus. For now, the abyss remains mostly unknown, not because it must be, but because we have not yet chosen otherwise. Its mysteries wait beneath our feet, while our attention often drifts skyward. The rarity of exploration is a mirror held up to us, showing not the limits of possibility, but the limits of our priorities. And as we leave this thought, we drift naturally into what the sea hides from history: shipwrecks, artifacts, and even entire civilizations swallowed by waves, resting quietly in the darkness until chance or curiosity brings them back into view. The deep sea does not only hide strange animals and alien ecosystems, it also holds our history. Every ship that has ever sailed and failed, every storm that has claimed vessels, every war that has sunk fleets has left traces that rest on the sea floor. Some lie in shallow waters, discovered and studied, but countless more rest in the abyss, where no diver can reach and only machines can glimpse. The ocean is as much an archive as it is an ecosystem. It preserves the wrecks of battles, the remains of trade, and perhaps even the hints of civilizations lost to rising tides. To descend into the deep is not only to study biology and geology, it is to wander through the graveyards of human memory. Shipwrecks are among the most haunting sights in the ocean. Unlike ruins on land, which crumble under weather, wind and sun, wrecks at depth are protected by darkness, pressure and cold. Without light and oxygen, wood and metal decay slowly. In some cases, structures endure for centuries almost untouched. The most famous example is the Titanic, lying at nearly 4 kilometers down. When it was discovered in 1985 by Robert Ballard and his team, the world was transfixed. Images of the great ship, split in two but still eerily intact, lying in silence, captured imaginations. The Titanic was not alone. Thousands of ships from wars, commerce and exploration rest beneath the waves, each with its own story frozen in darkness. Wartime wrecks are especially numerous. In the Pacific, remnants of World War II battles dot the seabed. Aircraft carriers, destroyers, submarines, and planes lie where they fell, their guns still pointing outward, their decks still holding relics of lives suddenly cut short. In some cases, vehicles and artifacts remain inside, preserved in the cold. To see them is to step back in time, not through a museum but through the real objects, untouched since the day they sank. For historians, these wrecks are priceless, offering insights into technology, tactics, and even daily life at sea. For families of those who never returned, they are graves, solemn reminders of sacrifice. Trade routes too left their marks. Ancient ships carrying amphorae, pottery and goods sank in storms and now rest in silence. Some of these wrecks date back thousands of years, still holding cargo that reveals the connections between distant cultures. In the Mediterranean, dozens of ancient wrecks have been found, their contents astonishingly well preserved. In deeper waters, where divers cannot go, robotic vehicles have begun to uncover even older sites. Each find expands our understanding of history, filling gaps with tangible proof of journeys, exchanges, and tragedies. But the ocean does not only preserve the ships that travelled on it. It may also conceal the lands that once bordered it. Sea levels have not always been what they are today. During ice ages, when glaciers locked water away, coastlines stretched farther outward. People built settlements on those coasts, lived by rivers that now empty into the sea, and walked landscapes that are today drowned. As the ice melted and seas rose, those settlements vanished beneath waves. Some archaeologists believe that enormous regions of human prehistory now lie underwater, undiscovered. One example is Doggerland, a vast plain that once connected Britain to mainland Europe. 10,000 years ago, it was home to rivers, forests, and people. As sea levels rose, it disappeared beneath the North Sea. Today, fishermen sometimes haul up bones, tools, and artifacts from its past. Mapping of the seabed reveals ancient river channels and ridges, a ghostly memory of a land once alive with humans. Similar drowned landscapes exist around the world, in the Gulf of Mexico, in the waters off India, in Southeast Asia. Each one holds the possibility of buried civilizations, erased not by conquest, but by the slow rise of water. The preservation of artifacts under the sea is sometimes astonishing. In cold, anoxic environments, wood survives, metals corrode slowly, and fabrics may even linger. The wreck of the Black Sea ship found in 2018, more than 2,000 years old, still had its mast standing and rudders intact. Preserved by the oxygen-poor waters of the Black Sea, it looked as though it could sail again, even though it sank centuries before Rome's rise. Such finds remind us that the ocean does not always erase, sometimes it guards. Yet the ocean is not a perfect vault. Salt corrodes, currents shift, and life colonizes. Wrecks become reefs, overgrown with corals, sponges, and fish. What begins as tragedy often becomes sanctuary, as marine life adopts steel and wood as habitat. Divers visiting wrecks often marvel at the abundance of life around them. A battleship may sink in destruction, but live on as a thriving reef, an artificial ecosystem sustained by what once was human ambition or folly. The duality is poignant. Wrecks are both graves and gardens, reminders of death and proof of renewal. The mystery of lost civilizations has always stirred the human imagination. Atlantis, the mythical city described by Plato, is perhaps the most famous example. While most scholars see it as allegory rather than history, the idea of a great city swallowed by the sea remains powerful. Legends from cultures around the world tell of floods, sunken kingdoms, and lands taken by the ocean. Some may be pure myth, others may reflect memories of real events, coastal flooding, tsunamis, or gradual sea level rise. Beneath the waters of our planet may lie truths that inspired those stories, waiting to be found. For modern explorers, the challenge is not only locating, but respecting. Wrecks are often legally considered war graves or cultural heritage sites. Disturbing them can be controversial, raising questions of ownership, ethics, and preservation. Some argue they should be left untouched, memorials to the lives lost. Others see value in recovering artifacts, conserving them, and sharing them with the world. Technology adds to this tension. ROVs can enter wrecks, film interiors, and even recover objects, but each intrusion risks damage. Each disturbance risks erasing part of the story. The balance between curiosity and respect is delicate. Beyond history, shipwrecks also remind us of our vulnerability. Every vessel that sank was once believed to be safe, every journey undertaken with confidence. The ocean proved otherwise. From ancient triremes to modern liners, from wooden canoes to nuclear submarines, all have been claimed. The sea is not selective. It humbles equally. To see their remains is to be reminded that no technology is immune, no human endeavour untouchable. For scientists, however, the study of wrecks is not just about human history. It also provides data about how materials degrade in the deep, how ecosystems colonize structures, how currents shape sediments. Wrecks become laboratories, natural experiments in long-term change. Each one adds to our understanding, not only of the past, but of the present. Imagine descending in a submersible and coming upon a wreck. The beam of your lights cuts through blackness, and suddenly a shape emerges, metal twisted, wood splintered, but still recognizably a ship. Railings, masts, perhaps even cargo hold shape. Fish dart in and out. Corals glow faintly and the silence is complete. It feels like trespassing in a place both sacred and eerie, a reminder that the ocean remembers everything. For a moment, you are not just exploring biology, you are exploring memory, touching the edges of human stories long forgotten. The ocean holds our triumphs and our tragedies, our ambition and our fragility. Every wreck is a chapter, every drowned land a verse. Together they form a submerged history parallel to the one we write on land. And as we pass through them in thought, we move onward into the present role the deep ocean plays, not only as an archive but as an active system regulating the planet's climate, shaping the atmosphere and guiding the future. When most people think about climate, they picture the sky. Clouds, storms, winds, and the warming atmosphere dominate the conversation. Yet the largest regulator of Earth's climate lies not above us but beneath the waves. The deep ocean, vast and hidden, acts as a stabilizer, absorbing heat, storing carbon, and moving energy around the planet in ways we rarely see but constantly feel. Without it, our world would be far hotter, our weather far wilder, and life as we know it would struggle to endure. The deep sea is not only a mystery of biology and geology, it is the engine room of climate. To understand its role, consider first the ocean's sheer size. Covering more than 70% of Earth's surface and plunging to depths greater than Everest is tall, it holds more than 90% of the planet's liquid water. Water has a high capacity to store heat, far greater than air or land. That means the ocean absorbs and redistributes enormous amounts of energy from the sun. Currents, both at the surface and in the deep, carry that heat from equator to pole, balancing temperatures and softening extremes. Without this system, the tropics would be unbearably hot, the poles even colder, and the middle latitudes far more volatile. Surface currents like the Gulf Stream are visible expressions of this system. They transport warm water northward, releasing heat into the atmosphere, moderating climates in Europe and North America. But beneath the surface lies another, slower and even more powerful system, the global conveyor belt, or thermohaline circulation. Driven by differences in temperature and salinity, this circulation moves water masses across the globe over centuries. Cold, salty water sinks in the North Atlantic, flows southward at depth, circles Antarctica, and eventually rises again in the Pacific and Indian Oceans. This cycle, though invisible to daily life, is one of the great engines of climate stability. The deep ocean also plays a critical role in storing carbon. Carbon dioxide dissolves into the ocean from the atmosphere. Some of it is used by plankton near the surface, then carried downward as organic matter sinks. This process, known as the biological pump, transfers carbon from air to sea, locking it away for centuries in deep waters. Without it, atmospheric carbon levels would be much higher, amplifying the greenhouse effect dramatically. The twilight zone, with its massive daily migrations of fish and plankton, acts as a conveyor, moving carbon downward each night. The abyss then becomes a vast storage vault, holding the planet's excess until slow circulation eventually releases it back. In this way, the deep ocean acts as a buffer. When humans burn fossil fuels and release carbon, about a quarter of it is absorbed by the ocean. That slows the rate of warming we would otherwise experience. The ocean has also absorbed more than 90% of the excess heat generated by greenhouse gases since the Industrial Revolution. Without this absorption, surface temperatures would have spiked far higher already. We live in a climate moderated daily by the deep, even if we rarely acknowledge it. But buffers have limits. The more carbon the ocean absorbs, the more its chemistry shifts. Carbon dioxide reacts with seawater to form carbonic acid, lowering pH. This process, called ocean acidification, affects shells, corals, and countless organisms. The deep ocean, once a stable vault, is slowly changing in ways we do not fully understand. Heat, too, is accumulating. Measurements show that abyssal waters are warming, even by fractions of degrees. That may seem small, but in a system so vast it represents enormous energy. Those changes ripple upward, altering currents, weather, and ecosystems. The very buffer that protects us may be straining under the weight of what we pour into it. The role of the deep ocean in climate is not a modern discovery, though our understanding has deepened with time. Ancient sailors knew currents mattered. Fishermen observed the link between ocean shifts and weather. The El Niño phenomenon, where warm water accumulates in the Pacific, has been felt for centuries in South America as floods and droughts alternated. Today, we know these patterns are connected to larger oscillations in deep circulation. The ocean is not separate from climate. It is climate. Every storm, every drought, every hurricane has roots in the movements of water as much as air. Studying the deep ocean's role is difficult. Sensors and floats must be deployed for decades, measuring subtle changes. Satellites can measure surface temperatures and currents, but cannot see kilometers below. ROVs and submersibles capture snapshots, not continuous records. As a result, our knowledge is still patchy, especially in the southern hemisphere and polar regions. Yet what we have learned makes clear that the abyss is not passive. It is active, dynamic, and essential to stability. The polar regions are especially critical. Around Antarctica, cold, dense water sinks, forming Antarctic bottom water that flows outward into the abyss. This sinking drives much of the global conveyor. If melting ice or warming disrupts it, the consequences could ripple worldwide. Slower circulation means less carbon storage, less nutrient transport, more regional extremes. The North Atlantic too is vulnerable. Fresh water from melting Greenland ice reduces salinity, weakening the sinking currents. Some scientists warn that this system could slow dramatically in coming centuries, reshaping climates across continents. The deep ocean is not invulnerable. It is a living system sensitive to change. For humans, the idea that the ocean beneath us quietly regulates the air above is both reassuring and unsettling. Reassuring because it shows resilience. The planet has mechanisms that soften our impacts. Unsettling because those mechanisms are finite and we are testing their limits. It is easy to forget the deep when we live on land. But whether we feel it or not, every breath, every harvest, every storm forecast is shaped by what happens thousands of meters below. The deep ocean's role as a regulator also expands our view of responsibility. When we think of protecting climate, we often think of forests, energy, and atmosphere. Yet protecting the ocean is just as crucial. Overfishing, mining, and pollution threaten not only ecosystems but the climate systems they support. A damaged twilight zone may weaken the biological pump. Disturbed deep currents may alter carbon storage. The connections are complex but undeniable. Caring for the ocean is caring for the climate, because the two are inseparable. The scale of it can be humbling. Imagine the abyss as a vast set of lungs, breathing slowly, taking in carbon, releasing it centuries later. Imagine it as a great thermostat, absorbing heat, redistributing it, preventing wild swings. Imagine it as a hidden river system flowing across basins, linking continents in a cycle that spans generations. These are not metaphors. They are real processes, measured by instruments, calculated by models, and felt in weather patterns across the globe. The deep ocean is the unseen engine of stability. For explorers, this adds another layer of meaning to their work. A dive is not only about discovering new creatures or mapping terrain, it is about glimpsing the machinery that underpins the planet. Each sample of water, each measurement of current, is a clue to how Earth maintains its balance. The mystery is not only biological but planetary, not only about survival in darkness, but about the survival of climates we depend on. And perhaps this is why the deep sea deserves more attention. It is not a remote curiosity, not just a stage for strange animals. It is a regulator we cannot live without, a partner we cannot ignore. To explore it is not indulgence, it is necessity. For without it, the air we breathe, the weather we endure, the future we hope for, all would be drastically different. As we carry this thought deeper, the image of the abyss shifts again. It is no longer only strange creatures or ancient wrecks. It is no longer only mystery. It is a vital part of the Earth's living system. But even as it regulates and stabilizes, it faces threats we have created. Pollution, plastic and waste now reach into its depths, turning the hidden regulator into a hidden victim. When people imagine the deep sea, they often think of untouched wilderness, a place so remote that human impact could not possibly have reached it. For centuries, that illusion seemed believable. The ocean felt infinite, able to swallow anything we discarded, able to absorb our mistakes and keep them hidden. But the truth we now know is that the deep is not untouched. It is marked, scarred, and increasingly burdened by our presence. Plastic, chemicals, and waste have reached even the deepest trenches, carried downward by currents, by sinking particles, by the relentless pull of gravity. The abyss has become a repository for our pollution, and the crisis it faces is as invisible as it is immense. Plastic is the most obvious symbol of this intrusion. It is everywhere in modern life. Bottles, bags, packaging, clothing fibres. Lightweight, durable and cheap, it was hailed as revolutionary when first invented. But those very qualities make it a problem. Plastic does not biodegrade in the way organic matter does. It breaks down slowly into smaller and smaller pieces, but it never truly disappears. These fragments, called microplastics, have been found in every corner of the ocean, from surface waters to sediments miles below. In 2019, scientists discovered microplastics in samples taken from the Mariana Trench, nearly 11 kilometres deep. The very deepest place on Earth is now contaminated by our waste. The path to the deep is deceptively simple. Plastics discarded on land or at sea eventually enter rivers, coasts and currents. Some float for years, drifting across basins in massive gyres like the Great Pacific Garbage Patch. Others sink, weighed down by algae, debris, or colonizing organisms. Once sinking, they may travel all the way to the abyssal plains, settling into mud that accumulates over millennia. Some are ingested by fish and plankton, moving upward and downward in the food web. With every pathway, plastic penetrates deeper, carried by processes far larger than we can control. Microplastics are especially insidious. Too small to see easily, they are eaten by zooplankton, which mistake them for food. From there, they move up the chain. Fish eat zooplankton, larger predators eat fish, and so on. At each stage, plastic fragments accumulate in bodies, sometimes leaching chemicals, sometimes simply occupying space that should hold nutrition. In the deep, where food is already scarce, ingesting plastic instead of organic matter can be devastating. Animals that spend enormous energy searching for meals cannot afford to waste effort on indigestible fragments. Yet they do, because the fragments are everywhere. Larger pieces of plastic create problems of their own. Bags drift into the deep, settling like ghostly jellyfish. Fishing nets, lost or abandoned, continue to trap and kill animals in what is called ghost fishing. Crabs, fish, and even whales can become entangled, sometimes fatally. On the seafloor, bottles, containers, and fragments litter the landscape. Remote cameras have captured images of soda cans resting among tube worms, of plastic bags clinging to vents, of toys and debris lodged in sediment where no human has ever walked. The effect is jarring, a reminder that even the most alien places on Earth are not beyond our reach. Pollution extends beyond plastic. Chemicals from industry, agriculture, and households wash into rivers and seas, eventually reaching the deep. Persistent organic pollutants, heavy metals, and radioactive waste all accumulate in sediments. Because the deep is slow to change, these substances can remain for centuries, locked into the mud but still affecting life. Studies have found PCBs and other industrial chemicals in amphipods from the Mariana Trench, animals that should have been isolated from human influence. The chemicals likely sank with particles of organic matter, carrying with them toxins produced half a world away. Oil, too, seeps into the deep, both naturally and through spills. When the Deepwater Horizon disaster struck in 2010, oil plumes spread not only on the surface, but deep into the Gulf of Mexico. Bacteria capable of digesting hydrocarbons bloomed, altering ecosystems in ways we are still studying. Other spills, smaller but numerous, have similar effects, adding invisible layers of contamination. Radioactive waste, once deliberately dumped in barrels offshore during the mid-20th century, has corroded over decades, leaking its contents into waters never meant to hold them. The ocean, seen at the time as infinite, was used as a dumping ground. Now we know that it is not infinite, and the consequences ripple quietly through its depths. The hidden nature of this crisis makes it harder to address. On land, pollution is visible. We see smog in the air, garbage on streets, rivers clogged with bottles. In the deep, pollution is out of sight, discovered only when scientists lower cameras or nets. By the time we see it, it has already spread far. The vastness of the ocean makes cleanup almost impossible. Removing plastic from trenches kilometers down is not feasible with current technology. Filtering microplastics from currents is equally impractical. Once pollution reaches the deep, it is effectively permanent. The consequences extend upward, because the ocean is not separate from us. Fish that ingest microplastics may end up on our plates. Toxins concentrated in deep food webs can move into commercial species. Currents that circulate heat also circulate contaminants, ensuring that no part of the ocean is truly isolated. Even the climate-regulating functions of the deep may be altered if ecosystems that drive carbon storage are disrupted by pollution. A twilight zone filled with plastic instead of plankton cannot function as it should. The hidden crisis is not only about animals, it is about planetary balance. Yet there is still resilience. Some deep-sea microbes have evolved the ability to digest certain plastics. Bacteria that consume hydrocarbons proliferate after spills, breaking down oil. Life adapts, as it always has, but adaptation is not unlimited. The scale of human waste far exceeds the capacity of natural systems to cope. For every microbe that can digest plastic, millions of fragments sink faster than they can be consumed. For every oil-degrading bacterium, tons of crude seep into sediments. The imbalance grows with each passing year. The awareness of this crisis is relatively new. For decades, few thought about where trash went once it left site. Only in the last 20 years have deep-sea surveys revealed the extent of contamination. Images of plastic bags in the Mariana Trench made headlines, not because scientists were surprised, but because the public was. The idea that the deepest place on Earth is polluted struck a chord. It shattered the illusion of untouched wilderness. The abyss is no longer a sanctuary. It is part of the same world we shape, for better or worse. Addressing this crisis requires action at the surface. Reducing plastic production, improving waste management, and developing biodegradable alternatives are critical. Regulations on dumping and pollution help, though enforcement is uneven. International cooperation is essential because the ocean is shared. No one nation controls its currents or trenches. What is discarded in one place ends up in another. The deep sea's contamination is a collective responsibility, a mirror of our collective behaviour. For individuals, the scale can feel overwhelming. What difference does one bottle, one bag, one choice make in an ocean so vast? The answer is that while individual choices matter, systemic change matters more. Industries, governments, and societies must shift together. But awareness is the beginning, and awareness grows with stories. Each piece of plastic photographed on the sea floor, each amphipod found with toxins in its body, each discovery of microplastics in the Mariana Trench builds the story. It tells us that the problem is real, present, and urgent, and in a way that urgency connects us back to the broader theme. The deep sea is not a distant world irrelevant to our lives. It is tied to us in every breath, every climate pattern, every meal of seafood. To pollute it is to pollute ourselves. To protect it is to protect our future. The crisis below is hidden, but it is not separate. As we leave this reflection, the deep once again reveals its paradox. It is fragile yet resilient, burdened yet still alive. Pollution may have reached even the trenches, but life persists. Microbes digest what they can, animals adapt as they must, and currents continue to flow. The abyss absorbs our waste even as it regulates our climate. But what else might it hide? If it can hold our pollution, it can also hold mysteries, perhaps even forms of a life beyond what we know, maybe even intelligence in shapes we have yet to imagine. Whenever people wonder about intelligent life beyond Earth, their thoughts usually turn to the stars. Telescopes scan the skies, radio dishes listen for signals, and imagination leaps toward distant planets circling distant suns. But sometimes, the more provocative question is closer to home. Could our own ocean, so vast, so unexplored, harbour forms of intelligence we have overlooked? Could there be beings in the deep, living in darkness, whose ways of thinking and communicating are simply too alien for us to recognise? It is a possibility that feels like science fiction. Yet when you remember that more than 80% of the ocean remains unexplored, the question no longer feels absurd. It feels unavoidable. When we talk about intelligence, we often frame it in human terms: language, tools, culture, abstract reasoning. By those measures, humans stand apart. Yet other animals clearly demonstrate their own forms of intelligence. Dolphins use complex vocalizations, recognize themselves in mirrors, and work cooperatively to hunt. Octopuses solve puzzles, open jars, and manipulate their environment in ways that suggest a remarkable problem-solving mind. Even fish, often dismissed as simple, show memory, learning, and social structures more intricate than once believed. If such intelligence can arise in the shallows and coasts, why not in the abyss? Octopuses are especially compelling examples. With distributed nervous systems, more neurons in their arms than in their central brain, they challenge our very definition of intelligence. They can camouflage instantly, not only in colour but in texture. They can learn by watching, an ability once thought uniquely human. They can escape enclosures, navigate mazes, and display curiosity in ways that feel familiar to us. Yet octopuses are not long-lived, most surviving only a few years. Imagine what a cephalopod might become if evolution granted it centuries, if conditions in the deep allowed it to grow larger, more complex, more enduring. The possibility is speculative, but not unthinkable. The deep offers unique pressures that could both hinder and foster intelligence. On one hand, the scarcity of food and energy may discourage large, energy-intensive brains. Survival often favours efficiency, patience, and minimalism. On the other hand, the darkness and vastness could encourage the development of unique communication systems. Bioluminescence, already widespread, might be refined into symbolic language. Patterns of light could convey information far richer than human speech, visible over distances where sound does not reach. Some squid already coordinate with light displays, flashing signals to one another. Could deeper relatives use similar systems in ways complex enough to count as culture? Whales remind us that intelligence does not always need tools. Their songs travel across oceans, carrying information we are only beginning to decode. Humpbacks change their songs over time, as if composing new verses. Sperm whales communicate in coded clicks, with dialects differing between groups. Some researchers argue these vocalizations could represent a form of language, though not one we yet understand. If intelligence exists in the deep, it may not look like tool-making hands. It may sound like songs, flash like lights, or feel like currents. Our inability to recognize it does not mean it is absent. The scale of unexplored habitat also matters. The deep sea is not small. It is the largest living space on Earth, dwarfing forests, deserts, and grasslands combined. If life exists anywhere, it exists there in abundance. Trillions of fish, countless invertebrates, whole ecosystems flourish unseen. To assume none of that life could have developed intelligence may say more about our lack of imagination than about reality. Given enough time, enough diversity, and enough niches, The emergence of minds capable of awareness seems less like fantasy and more like probability. But what would such beings look like? Our imagination, shaped by human experience, tends to picture humanoid forms with eyes, arms, and recognizable expressions. The deep sea likely offers none of that. An intelligent being might be gelatinous, drifting rather than walking. It might perceive with sonar or electricity rather than sight. It might live communally, its intelligence spread across a colony rather than contained in an individual. It might not even value what we call individuality, instead existing as networks or swarms. To us, such intelligence might go unrecognized because we do not know how to measure it. There is also the issue of contact. Even if intelligent life exists in the deep, it may not wish to meet us. Our machines are noisy, blinding, intrusive. Submersibles flood the dark with artificial light. Startling animals adapted to dimness. Sonar blasts echo painfully across basins. Nets scoop indiscriminately. From the perspective of deep-dwelling beings, our presence might be destructive, confusing, even hostile. If intelligence lurks there, it may avoid us deliberately, retreating into depths we cannot easily reach. Silence, in that case, would not mean absence, it would mean choice. Speculation aside, the search for unknown intelligence in the deep is not entirely unfounded. Scientists already investigate signals and patterns for signs of complexity. Some bioacoustic research on whale communication treats their clicks as potential coded language. Bioluminescent patterns are being studied for rules, repetitions and structures that might hint at symbolic meaning. While no evidence yet suggests a hidden civilization, the act of searching itself expands our view of what intelligence might be. It forces us to abandon human-centric definitions and consider broader possibilities. Even myths echo the idea. Stories of sea spirits, mermaids, and underwater kingdoms may not have been based on literal beings, but they reveal a deep-seated human intuition that the sea is too vast, too alive to be empty of minds. Ancient sailors sensed presence in the waves, even if they could not prove it. Today, with machines and science, we sense the same presence in data and glimpses. The unknown remains, and intelligence may be one of its shapes. The thought that Earth might host more than one intelligent species in parallel, humans on land, others in the deep, is both thrilling and unsettling. It would redefine our place, not as singular, but as one among many. It would challenge our assumptions about dominance, about uniqueness, about what it means to be alive and aware. Even if no such beings exist, asking the question forces us to confront the limits of our imagination. It reminds us that we know so little, and that mystery itself is a kind of mirror. For now, all evidence points to mystery rather than proof. We have no recordings of languages, no artifacts of technology, no structures on the seafloor that hint at hidden societies. What we do have are creatures that already display intelligence. Octopuses, whales, dolphins, showing that the ocean is fertile ground for minds. Whether deeper forms exist remains unanswered, but the question, left open, gives the deep an added layer of wonder. We look outward for aliens. Perhaps we should also look downward. And as we leave that thought behind, the perspective widens. Whether or not unknown intelligence exists, the deep remains the last true frontier of Earth, a place as unexplored as other planets, yet part of our own home. Its mysteries, biological, geological, even philosophical, still call us, reminding us that the final unknown lies not above the sky but beneath the waves. When people talk about frontiers, they often speak of mountains, deserts, or space. These are the places that seem to push against the edges of what is known, demanding courage and invention to cross. Yet the greatest frontier is not distant. It lies beneath the surface of the ocean, covering most of our planet yet remaining largely unseen. The deep sea is Earth's last frontier, not because we cannot reach it at all, but because reaching it fully requires more than we have so far chosen to give. It is vast, hidden, and filled with mysteries that challenge our imagination as much as they challenge our machines. The phrase, "last frontier," suggests a boundary between what we know and what we do not. In the case of the ocean, that boundary is staggering. More than 4/5 of the seafloor is still unmapped in detail. Species are discovered on nearly every expedition, many of them so strange that they force us to reconsider the definitions of entire groups of life. Geological formations from trenches deeper than Everest's tall to volcanic mountains larger than any on land remain unseen. The truth is that we have only skimmed the surface of understanding. For all our satellites, submarines and sonar, we are still newcomers peering through a narrow keyhole into a cathedral. What makes the deep sea a frontier is not only its physical inaccessibility, but its intellectual vastness. Every discovery there forces us to revise assumptions about biology, chemistry, and even the origins of life. Hydrothermal vents showed that ecosystems can exist without sunlight, rewriting our understanding of energy flow on Earth. Bioluminescence revealed that darkness is not emptiness, but a canvas filled with communication and deception. Gigantism and dwarfism showed that scale is malleable, that evolution stretches and compresses forms in ways we did not expect. The deep is not just another ecosystem, it is a crucible of new rules. For humans, frontiers carry meaning beyond science. They are metaphors for curiosity, for exploration, for the urge to go beyond what is safe. Space has long held that role, inspiring generations with images of rockets and astronauts. But the deep sea is no less deserving. It is as alien as Mars, as challenging as the moon, and far closer. It holds answers not only about other planets, but about our own. If the story of exploration is about facing the unknown, then the abyss is our most immediate and enduring test. And yet, it is a frontier we often overlook. Part of that is psychology. The sky feels open, inviting, full of promise. The sea feels closed, heavy, intimidating. Darkness and pressure do not stir dreams in the same way rockets do. But if we set aside emotion and look at reality, the abyss offers everything a frontier should. Challenge, wonder, discovery, and the chance to redefine ourselves. It is not only the last frontier of Earth, but perhaps the most profound, because it exists within our home yet remains beyond our grasp. Explorers who descend into it often describe feelings that echo astronauts. Awe at the scale, humility in the face of forces greater than themselves, a sense of seeing something no human has seen before. These are the hallmarks of frontier experience: to float in a submersible, lights cutting into blackness, and suddenly glimpse a creature unknown to science is as powerful as gazing at Earth from orbit. Both experiences strip away arrogance and replace it with wonder. Both remind us how little we truly know. But unlike space, the deep sea connects directly to our survival. It regulates climate, cycles nutrients, sustains fisheries, and shapes weather. Its mysteries are not distant curiosities. They are immediate, practical, and urgent. To treat it as a frontier is not indulgence. It is necessity. We cannot claim to understand our planet while leaving most of it unexplored. We cannot prepare for the future while ignoring the systems that stabilize it. The frontier is not optional. It is central. The scale of what remains unknown is hard to overstate. Estimates suggest there may be millions of undiscovered species in the ocean. Some are microbes, shaping chemistry in ways we do not yet grasp. Others may be larger, stranger, hidden in trenches or drifting unnoticed in open waters. Each expedition brings new forms: translucent fish, gelatinous predators, worms with metallic bristles, microbes that consume gases we once thought uninhabitable. Each one is a reminder that mystery is not behind us but beneath us. The frontier is alive, not historical. For culture, the deep sea as frontier carries resonance too. It is the place where myths of monsters, Legends of lost cities and dreams of alien life converge. It is the setting for stories of krakens, Atlanteans, mermaids, and gods of the underworld. The frontier has always fueled imagination, and the abyss is fertile ground for it. But unlike pure myth, this frontier holds truths that rival the wildest fiction. Giant squid exist. Hydrothermal vents glow. Bioluminescent fields light the dark like galaxies. These not dreams but realities, waiting only for us to look. The frontier is also moral. How we choose to explore and use the deep reflects who we are. Already, mining companies eye the metals in vents and nodules, promising profits, but risking destruction of fragile ecosystems. Nations compete quietly for rights to seabeds, seeing them as resources to be exploited rather than mysteries to be respected. In this sense, the deep sea is not only Earth's last frontier, but a test of whether we have learned from past frontiers. History shows us how often exploration became conquest, how often wonder became plunder. The abyss offers us a chance to do differently, to explore with humility and care, to value discovery over extraction. The notion of frontier also carries time. Unlike mountains which we can climb, or forests which we can walk, the deep sea will take decades, perhaps centuries, to fully explore. Each step forward is slow, costly, and limited. That slowness may be frustrating, but it is also a gift. It ensures that mystery lingers, that wonder remains alive. The last frontier is not one we will exhaust quickly. It will accompany humanity for generations, a reminder that no matter how much we learn, there is always more. For individuals, the frontier is not only physical, but symbolic. To think of the deep is to confront our own relationship with the unknown. Do we turn away, content with surface knowledge, or do we face it, curious, willing to step into darkness? The answer defines not only exploration but our sense of ourselves. Humans are creatures of frontiers. We thrive on challenge. The deep offers it in abundance, waiting not with hostility but with silence, ready to reveal itself to those who dare. Imagine standing on a shoreline, gazing out at the horizon. The waves roll in endlessly, but beneath them stretches a space larger than all continents combined. That space is not mapped, not fully known, not fully understood. It is a frontier you can see every day, yet rarely think about. To acknowledge it is to realize that exploration is not only for astronauts and faraway planets. It is for us, here, now, in the waters that surround us. The deep sea as Earth's last frontier reminds us of two truths. First, that our planet is still wild, still mysterious, still larger than we imagine. Second, that our role is not only to inhabit it, but to seek it, learn from it, and care for it. The frontier is not about conquest, but about humility, about recognizing that even at home, we are still explorers. And as we leave this reflection, we prepare for the final thought of the journey. Beyond all the details, all the science, all the history, the deep sea remains a mirror of mystery, a place where our questions reflect back at us. To close, we turn not to answers, but to wonder itself, carried on the currents of an ocean we barely know. As we arrive at the end of this long journey into the abyss, it is tempting to imagine closing the book neatly, tying together all the threads with a single explanation. But the deep sea does not work that way. It resists closure, it resists certainty. What it gives us instead are reflections, glimpses that are as much about ourselves as they are about the ocean. When we peer into its darkness, we find not only creatures and currents, but mirrors, surfaces that reflect back our own questions, our own fears, our own longings for meaning. The deep is not only a frontier of Earth, it is a frontier of the mind. We began by looking at the ocean as unknown space, a place larger than continents, yet less familiar than distant moons. Along the way we found layers of strangeness, pressures that crush, darkness that hides, creatures that glow, vents that breathe, and stories that humans have told for centuries to explain what they could not see. We discovered that the abyss regulates our climate, that it absorbs our waste, that it holds our history, and perhaps even that it teases us with possibilities of intelligence we cannot yet recognize. Each revelation added detail, but none erased the fundamental mystery. If anything, the deeper we went, the more the questions multiplied. The ocean as a mirror shows us how limited our perspective can be. On land, we assume light is essential, yet the deep thrives without it. We assume life requires warmth, yet vent communities thrive in cold darkness punctuated by scalding jets. We assume scale is fixed, yet the abyss produces giants and miniatures side by side. We assume intelligence must look like ours, yet octopuses and whales remind us that other minds follow different rules. Each assumption, overturned, reflects our biases. The ocean reminds us that our view of reality is narrow, shaped by what we happen to inhabit. Beyond that, other ways exist, waiting silently until we care to notice. There is also a lesson in humility. For centuries, humans imagined themselves as masters of Earth, cataloguing, mapping, claiming, and yet the majority of our planet remains unmapped, unexplored, unseen. The deep sea laughs gently at our confidence. It shows us that we are not as knowledgeable as we think, that mystery still outweighs certainty, that humility is not defeat, it is opportunity. To realize how little we know is to realize how much there is still to discover. The ocean, as mirror, reflects not our mastery but our potential. It reflects our fears too. The stories of krakens and sea serpents were not just about animals, they were about helplessness, about facing forces too vast to control. Even now, when we speak of pollution, of rising seas, of changing currents, the ocean reflects back our anxieties about the future. It is both ally and threat, stabilizer and storm. To look at it is to confront fragility, both of the environment and of ourselves. That confrontation is uncomfortable, but necessary. Without it, we risk denial. With it, we face reality honestly, and perhaps act more wisely. The ocean also reflects our creativity. Its darkness invites imagination. Its silence invites stories. Myths of Atlantis, mermaids, gods of the sea, these were human attempts to give shape to mystery. Today, our imaginations take other forms, in films, in novels, in visions of alien oceans beyond Earth. The deep inspires art as much as science, dream as much as fact. That duality is important. Exploration is not only about instruments and data, it is also about wonder, about the spark that keeps curiosity alive. Without wonder, science is dry. Without science, wonder is blind. The ocean mirrors both, balancing them like tides. There is an irony here too. We dream of other planets, of colonizing Mars, of reaching stars, while beneath our feet lies a world equally alien, equally challenging, equally beautiful. The mirror of the ocean shows us our tendency to look outward instead of inward, to value distant mysteries more than local ones. Perhaps that tendency says something about our restlessness, our desire for horizons. But perhaps the ocean reminds us to balance, to seek stars, yes, but also to know our own home, to understand the planet that sustains us. The last frontier is not either or, it is both. The ocean reflects time as well. In its depths are archives of history, shipwrecks, drowned coastlines, sediments recording climate for millennia. It holds memories long forgotten by human societies, waiting quietly for rediscovery. But it also reflects the future. Its currents will shape weather, its chemistry will shape climate, its health will shape survival. The choices we make now about pollution, about exploitation, about exploration are all written into its waters. The mirror shows us not only what we are, but what we may become. What is striking, when you think about it, is how often the ocean mirrors paradoxes. It is fragile yet resilient, hostile yet nurturing, empty yet abundant, silent yet full of voices. Each paradox reflects our own contradictions. We are destructive yet creative, arrogant yet humble, fearful yet curious. The abyss becomes a metaphor not because we force it to be, but because it already is. In its vastness, it naturally echoes the contradictions of human existence. And so, as we bring this journey to a close, the mirror does not fade. It lingers, like the afterimage of light when you close your eyes. It asks not for answers, but for attention. The ocean does not need us to solve it in one sweep. It needs us to notice, to care, to act with humility and respect. It will remain mysterious long after we're gone, but our relationship with it will define how we live and how we leave the world for those who come after. Imagine, for a moment, standing again on a shoreline. The waves roll in, endless, indifferent, carrying light on their surface but hiding darkness below. You cannot see what lies beneath, but you know it is there. Vast plains, towering vents, glowing creatures, sunken ships, rivers of current, and maybe even minds you cannot recognize. You look out, and the ocean looks back. In that reflection, you see mystery, and in mystery, you see yourself. The story of the abyss is not finished. It never will be. It is not a book to close, but a horizon to keep returning to. Every expedition adds a sentence, every discovery a page, but the volume remains infinite. The deep will always hold more than we can grasp, and maybe that is the point. To live with mystery is to live with humility. To explore it is to honor curiosity. To protect it is to honor life itself. And so, as we step away from the abyss in thought, we carry with us not final answers, but a sense of wonder. The ocean is not only a part of Earth, it is a mirror of Earth, a mirror of us. When we gaze into it, we are reminded of how much lies unseen, how much remains possible, and how deeply we are tied to the unknown. That mirror is not something to fear, but something to cherish, because in its reflection we find both mystery and meaning, both the planet's story and our own.